Good afternoon. Um, Today we continue or with the applications of deep learning models in the image domain. There is still some things that we need to discuss with regards to convolutional neural networks. We just gave the introduction on that last week, so today we finished that up. Depending on time, we can already get started or already be on our way in starting the unsupervised modeling section as well, but we'll see where we get. First of all, like always, bit of news tidbits from the past week. So things are happening fast in LLM land and in multimodal land. Google has published an experimental version of their Gemini 2 Flash model, which turns out to be really at the forefront in terms of image consistency and image understanding. Of course, pundits at Twitter have already been saying, well, you don't need Photoshop anymore. Now we have something which is really good enough where you can, and here you see like a couple of use cases, like start with this image and I want to have like a glitch retro wave filter, or start with an image which is full of watermarks. Please remove the watermarks from this image. So this thing has gotten quite good. People have been gathering a lot of examples about this as well. For instance, one other fun example is next time you're late for work, you just take a selfie of yourself standing in front of your bathroom with your coat on, and then you say, well, basically, I would like to change this selfie so that it's me standing in front of a subway sign with the current date, March 13, 2025, on top of that as well, which is pretty cool about this model. I mean, you can basically take a selfie and put yourself somewhere else, but also the fact that it's pretty good at generating text is something that we haven't seen that much with these kinds of models yet, and this Gemini model seems to be very good at this as well. So pretty impressive stuff. There are a couple of other examples, like here is someone that shows that you can even make like animations and that it stays like relatively coherent in a certain style. Other things like it's pretty good at reasoning about images, like you give it this image and you ask it what is missing, and it knows that this is an incomplete sunglasses and that this is missing one of the lenses. And so on and so on. Here is a person like developing food pictures with Google Gemini. Yeah, I have two pictures. I would like this girl to hold the teddy bear. Yeah, no problem. So this thing is doing very well all in one tool. You can play with it yourself in Google's AI Studio. The model is available there, so you can try the Flash version of Gemini out and do these sort of things yourself as well. So that's already available now. What else have we seen? Yeah, last week I told you about a diffusion-based approach for a large language model. And I said, well, people had tried that previously, but it didn't seem to work that well. But theoretically speaking, it has a couple of benefits, mainly the fact that you can generate text way faster. So your inference is way faster. So there was this Mercury model last week. Today, so again, this is going fast. Other people have jumped on top of this, and they have already came up with something which they call block diffusion, which is basically an interesting mix between, you could say the best of both worlds. So where normal LLMs are autoregressive, so they just generate the next token in a sequence, but for which we know that they are high quality models. They give good output text. They can generate for as long as we want them to generate. We can apply smart key value caching strategies on top of this as well. But key problem with these autoregressive LLMs is that they're not parallelizable in inference. They're parallelizable during training, but not during inference, because you have that autoregressive aspect going on there. So you always need to wait for a token to come in order to stick that token in the input sequence and then have it predict upon itself. Then last week we saw a form of a diffusion model where it basically generates a whole bunch of text or diffuses a whole bunch of text at the same time, which is highly parallelizable, so that's fast, but it's not as good in terms of quality. You need to determine a fixed length up front, has no key value caching, so it has a bit of drawback. So of course what are people doing now? They're combining both approaches, and they're combining both the autoregressive approach with the diffusion approach by just simply diffusing in blocks. I say simply, of course implementation is a bit tricky, but that's kind of the next step that people have been working on. And Hugging Face has a nice outline or blog post or paper description about this idea. So also very new, basically just hot off the presses, and let's see if this model will replace the transformer-based architectures in a couple of months from now. After DeepSeek, also another Chinese giant the search engine company Baidu has released a couple of new models which they name Ernie 4.5 and Ernie X.1, which again, or they claim at least, that the performance is on par with DeepSeek R1, and again has been able to slash the price or cut the price in half again. And DeepSeek was already a relatively cheap model, so also we see that a lot of these Chinese tech giants are still competing in the race for fastest model, best model, cheapest model, and so on. So that will also be pretty interesting. And they compare themselves with the price that GPT 4.5 asks. And of course, yeah, for GPT 4.5, you pay a fee of $200, which is, there is no base subscription fee with Ernie 4.5. Google has also been busy not just with Gemini, but they have also released Gemma 3. And according to them, so they also kind of hard at work. And they say, well, this is the most capable model that we have that you can run on a single GPU or CPU. So this is something that you can run on a commodity laptop. I've been trying it out myself. It delivers state-of-art performance, outperforming Llama 3. Llama 3 with 405 billion parameters. It outperforms DeepSeek V3. It outperforms O3 Mini. And it's on par, let's say, with DeepSeek R1. It has support for multiple languages. It has support for agentic workflows, so it can use function calling. It supports function calling in there as well. So you get, again, a version of a model, and we saw this last time with Microsoft's Feline as well, where models are small enough that they can run on commodity machines. I mean, 27 billion parameters is really not that large compared to the 400 or 600 that you would normally need. And its performance is just behind DeepSeek R1, but better than all of these other models that you see here. It's already available in Ollama, so you can just pull the model down, run it on every kind of modern GPU or modern Mac. This should be relatively easy to run. And a pretty capable model, also works well to integrate in VS Code to help you with coding and things like that. So also for coding tasks, this is a model which is quite good. More details are in the paper that they propose as well. It's again a multi-model addition to the family of Gemma models, as most models that companies work on nowadays are. They come in different sizes, with the largest one being 27 billion parameters, but which is still quite reasonable. They are trained using data distillation and model distillation, which is also something that we saw recently, where you basically utilize a strong model that already exists to generate examples that you give to this model that you're still training. So you use kind of a teacher-student style setup where an already trained model is being utilized to speed up the training of a new model that you're basically building. That's also quite common nowadays. So more information in the paper. There is a lot of interesting stuff in there that they are playing with, but very capable model that Google also has released. So Google is not yet disappearing from the scene. They're also still doing a lot of interesting stuff. So the fight between these models and these companies is still very much ongoing. A person has also been implementing a model context protocol implementation. An MCP, model context protocol, is basically something that Anthropic has came up with, the company behind the Cloud LLM, where they say, well, it's time that we need some sort of generic framework where if you want to use an LLM with whatever tool that you have, that we have some standardized way that tells you how to write middleware that can connect the agent, the language agent, to this particular tool that you're interested in having it use, so that they can communicate in a standardized way, that maybe the tool can inform the LLM, hey, here is a list of functions that you can call from me, so if you want to utilize them, please use this schema, use this naming, use this function call in your output, and then I will give you the appropriate results back. A random person has basically been working on making an implementation for a Blender, and Blender is an open source 3D modeling package, and has been trying to set this up to connect this to Claude in this case. So you can download the repository yourself. Basically, it's pretty easy to link into a Claude interface. And then basically you get interesting things such as you can ask Claude, please generate me a 3D model of a lighthouse, for instance. And other people have been playing around with other examples in this space, and it does a surprisingly good job, even with only a rather limited set of functions that were exposed through this MCP middleware. On the left-hand side here is what Claude has generated. On the right-hand side is what you get if you utilize a model that converts a 2D image into a 3D mesh, which is also something that we have already seen previously. What's the difference if you look at the mesh structure, for instance? The Claude generated one is because it directly interfaces with Blender's primitives, is way more low poly, is way more efficient, versus the right one is a result of a model basically first generating in many cases some sort of point cloud or a signed distance field, and from there then, or a neural radiance field, and then from there extracting a mesh from it. But those meshes tend to be way more detailed, even for simple objects that might not need all of that detail. So there is value and there is benefit, and another benefit is that you can basically use a language model that you already have and start linking that into your tooling. So that's also quite interesting. Now there exists, like I said, there are a couple of other examples in here as well. Let's see, maybe I can find, do I still have some open? Probably not. No, I think I have some on the Blender MCP, on the slides probably. So yeah, you can see that people have been doing, or have been, so this is also a good example. On the right-hand side, you see basically Claude interfacing and going through its start process and basically interfacing with Blender on the left-hand side. Here is another example of an interior scene that someone has been working on with this thing. And there are many other examples as well, like a tree scene and so on. So this is getting pretty cool for asset development, for modeling development and so on. And basically, thanks to Anthropic for making this MCP protocol available, it's a good idea to do this. Now end users can get started by trying to implement an existing language model with tooling that you already have. Of course, this only works because Blender itself has a Python interface that you can utilize to extend the program with or to interface with the program. If it's just a graphical user interface, there would be some intermediate step or an additional intermediate step that you would need there. Speaking of models being or operating in an agentic fashion, so this has also been exploding. I think last week I showed you Manus AI, and by now it's also clear that under the hood they're actually utilizing Claude as their base model, and they're basically just prompting it in clever ways. Not that that's bad, but they are using another already existing model as their base model. But now we have also seen Gemma 3 can be utilized in an agentic fashion, as just mentioned. There, Cohere has done or has released models in this space. Command A is a model of last week that tries to be agentic. So all of these models are getting more and more capable. If you're wondering or doubting, like, okay, what does that mean? An agentic model. The idea is basically that they're able to get a task and then set off on their own to create a plan, interface with functions, interface with a computer interface, interface with a web browser in many cases, interface with the file system, and basically just go ahead and run on their own for a little bit until they produce the result for the end user. Manus has already or is announcing that they will make their thing available for everyone relatively soon. But meanwhile, the open source community has already been working on things such as all, so that you can take a base or an agent or a language model that you already have, something like Gemma, and then basically link that up with a web agent, a search agent, a coding agent, and so on to help you in your tasks. So you can set this up yourself should you want to. Of course, it's a bit more work, but these tools already exist. So that's also going on and rising rapidly in terms of a hype around this topic. Okido. Back to CNNs. So back to kind of a simpler vision model, let's say, but can also work, and at least this definitely can run on most commodity hardware. So last time we had a look at the very basic AlexNet, I believe. Yep, AlexNet architecture, where we saw we have these convolutional units that create these filtered output maps. We have this downscaling operator that we apply, and then we have the fully connected units at the end, and that was basically our whole architecture. So this was downsampling. We took a look at this 3D visualization last time as well. And then so that's the basic architecture. The next steps to discuss are basically then to take a look at a couple of further, let's say, variants that people have created or come up with for this basic CNN setup. There are more than just these. These are kind of the important milestones. So I already said last time in our history overview that LeCun had already been experimenting with convolutional neural networks in the 1990s, but they were difficult to train, and especially difficult to train if you have large layered networks like these. AlexNet is then the one that really popularized them again. And then the next steps were basically yeah, kind of a cycle, and quite similar as what we see with large language models as well. You always go through a step where you first try to check out what your scaling laws look like, meaning that you try to make the model larger, basically. You try adding more layers, and you try adding more parameters, and you try training them for longer, and you try adding more data until they start to fail. And that's then typically a step where people will go, okay, we have hit kind of the limits of this current architecture. Can we be smarter in the way how we set up our architecture? So VGG was basically, let's make it larger with 140 million parameters, already quite largely sized. And then ResNet introduces a new idea, the idea of residual connections in this case, which then allows to take another leap forward and to, again, make the models more capable, and very often make them as capable as the previous iteration of these models, but with a smaller parameter size, which is exactly what we see happening in large language modeling with these things like Gamma 3 as well. Models like SqueezeNet, MobileNet, EfficientNet, they go a step further. They, again, 50 times fewer parameters, leading to a small model that is easy to deploy on smart devices. And same for MobileNet, same for EfficientNet. Now, as a baseline, ResNet is and still, or was and still is, very popular as kind of an approach that we have figured out works for convolutional neural networks. And the idea is there that you add in residual connections. So nothing blocks you in a neural network layer setup that you need to add in your layers sequentially, one after the other, and that you only have connections between a layer and the units in a previous layer. You can also set up connections in this way, for instance, where you have your normal weight layer, you do a ReLU activation function, you have another layer of weights, and then basically you would have your output is that you say, well, I'm also going to take the inputs that I received in the layer previous to here and add them to the outputs that this layer produces. For stochastic gradient descent, this makes no difference. It's not that you're introducing a cycle, right? And as long as you have a directed acyclic graph, your gradients can flow from the output and can backpropagate through these different weight layers. The reason why this helps is, again, because of the problem of vanishing gradients. We saw that ReLU can already help a little bit there, but when you make your networks too large or too deep, again, you start encountering like decaying effects there, or you start running into problems there. So skip connections, they provide a more direct path for the gradients to reach these first layers, those layers that are on the left-hand side of your architecture. And basically, this is what then allows the training of these models to be improved again. Yeah, once you do that for a couple of steps or a couple of layers, you can then take this idea to the full extreme, and you can question, okay, what happens if we add in as many skip connections as we can? So we add in residual connections to all upstream layer blocks. Then you get something that's called DenseNet, basically. That looks like a spaghetti ball of skip connections. So this also works, but that's maybe a bit too extreme, maybe not necessary to make it so dense. What's another thing that you can do once you introduce skip connections is that you can apply a concept called layer dropout. We haven't seen what dropout is yet, but it will basically mean that we will drop out certain neurons out of our network during training. We'll get back to that in a second. But in an ordinary network like here, if we would want to drop out a complete layer, let's say F2 in this case, we can't really do so, because then we would break the connection from the right-hand side to flow through the left-hand side. My model would not learn anymore, right? Would stop training, would not be able to be trained anymore. So we would have, or we will have to, even if we apply the concept of dropout in an ordinary network such as this one, we can't really remove neurons from this network. So we will have to find another way to basically apply this mechanism of dropout. If you have residual connections, then you can basically effectively delete or drop out complete layers of your network during training, which is another kind of benefit that you get there. For if you would like to look at, okay, what's now a summary of all the best practices that people have come up with and that we have found work, there is a paper from a couple of years ago called A ConfNet for the 2020s, which basically tries to take all the best practices and places them together in a paper like which activation function should you utilize. Is it a good idea to use a stride of 2 for your convolutional units? Probably not. Is it a good idea to use more layers with smaller kernel sizes or less layers with bigger kernel sizes? Probably more layers with smaller kernel sizes. Is it a good idea to use residual connections? Yeah, sure it is. So this paper tries to perform like a benchmark experiment and bring all of that together. And actually the tutorials that you find on the webpage of Keras, for instance, about vision, they also take these good practices and they have a couple of tutorials that will lead you to a network that will already be quite a good starting point, given that you want to train your network from scratch. As you know, for the assignment, you're also free to take a pre-trained network, and maybe that might be necessary given the small amount of images that you actually have and given their size and so on, and that you start by fine-tuning a pre-trained network instead, or you try to do something like that. Or you try maybe asking Gemini 2 or Gamma and seeing what that does. Maybe that would also do a good job. So what is dropout? So this is another key element that the AlexNet paper had to introduce, apart from utilizing ReLU. Dropout was one of the other kind of key contributions that they made there. And that is basically a way to mitigate overfitting. And if you look at this AlexNet architecture, if we go all the way back to this figure, where overfitting can especially occur is in this massive bunch of dense layers that we have at the end. These two dense layers with 4,096 neurons each, right? It's already 4,096 times 4,096 weights for this second layer over there, plus bias weights. So probably these dense networks, you want them to have a lot of units in order to learn enough patterns and fit your data as well as you can. On the other hand, it's especially these dense layers that are quite prone to overfitting. So how do you fix that? One way is to apply regularization, right, where you add an L1 or an L2 term to your loss function. Dropout is another way that can help you to mitigate overfitting. And the idea is that for a certain layer, let's say, on which we want to apply dropout on, so let's say we have our two dense layers over here, and this is our final one with these 1,000 classes, and let's say we want to apply dropout on this layer of neurons. What dropout will do is that for each mini batch of training, so for each 64 instances that we're passing through our network, effectively what we would like to do, and it's a bit counterintuitive at first, is that we take a random sample of the neurons that we have in this layer, let's say maybe a random 30%, that's up to the user to configure, and we just remove them in this network for that mini batch of training. The problem, or problem number one here, is that we can't actually remove these neurons from our network. You could say, why not, as long as we retain just one neuron in this layer. That neuron is producing an output, right, and gets connected to the 1,000 neurons over there. So you could still have a gradient flow that goes from right to left and update and at least the weights for these connections and for the connections that this neuron receives. But the problem here is mainly due to the fact that when your software library inspects what your architecture looks like and passes that on or makes or prepares that for the GPU to perform training on, that it will typically assume that the sizes of your layers, the output sizes of your layers, will not change within the instances of or over the mini batches of training. So you have 4,096 outputs there. It will expect that it's always 4,096 outputs exactly. So how can you kind of simulate dropout then without really dropping out the neurons themselves? Well, you basically just say, okay, for the neurons that I consider to be dropped out, I will just force there or override the outputs that they provide them to be zeros instead. Right? So it is as if they have no activations going on there. And hence, if I then apply backpropagation, the weights that are connected to these neurons will also not be updated because I've basically overridden or I'm basically skipping the updates of their weights. So for the forward paths, I can just set their activation to 0. For the backward paths, I just skip over them when I'm updating their weights, right? It's still something that I can choose to do. In every mini batch, I pick another set of nodes to drop out, so to force them to have a 0 activation value. The gradients only flow through the neurons that are active. Once I'm done training, I stop with this dropout idea. Once my network is trained, I don't apply dropout anymore. So when I ask my network to perform predictions on new images, basically I'm not going to drop out neurons anymore. So I use all of them. But there is a bias that has crept into this setup, and the bias is, well, during training, basically if you look at the distribution of activation values that comes out of this layer, it's going to look suspiciously, or if I am always dropping out 30% of the neurons, and hence I'm setting their activation values to 0, like I will have a larger than normal peak around the 0 here, because 30% of my activation outputs that I get there is always 0, right? If I then apply something like batch normalization to re-normalize the intermediate outputs, it will be based on this distribution that I get there. During testing, I use all my neurons again, so my distribution is probably going to look a bit wider now, right? I will have less mass around 0 because I'm not forcing 30% of my neurons to provide an activation value of 0. If I then apply batch normalization or layer normalization with the rescaling mean and standard deviation that I have observed during training, I will end up doing an incorrect normalization because now I'm not dropping out 30% of my neurons. So typically, once you go for inference, you have to reduce the activations, you have to rescale them by a factor manually, or that's what your software library will do. And then this is also the main reason why for most libraries like Keras or PyTorch, in PyTorch you have a toggle to switch your network into a trainable mode and into an evaluation mode. The key thing that this does is basically informing the underlying software library, take care, now you shouldn't apply dropout anymore, and you should apply this rescaling factor instead. Right? And when you want to continue with training, you can do that, but then again, you need to apply dropout and not apply that scaling factor. What is the idea, or what makes this work? Why does this help to decrease overfitting? Well, obviously because you're forcing the network to learn something, but in every mini batch, you're kind of effectively taking away some of its neurons, right? And this will force your network. It's kind of like you learn an ensemble model of different sparser networks. You force the layer, each neuron, each unit in this layer to be important in its own right. You try to reduce node interactions. You try to have them learn, or have these different neurons in this layer learn different redundant pathways or different redundant representations to fit your data, and this will lead to better generalization. So again, it is kind of similar to an ensemble effect. Also there we saw, okay, you add in diversity and you have different sparser networks or different sparser models, and that also helps in that case. So typically, because it's the fully connected layers that are so sensitive to overfitting, that typically we apply them there. But you can theoretically apply dropout in other layers as well. You could also apply them in a layer of convolutional units, and maybe there have some of the filters generate a 0 convolution map by randomly removing one of the filters in each mini batch during training. So you can also apply dropout on other layers, but the fully connected layers are the most commonly, or the ones where this is most commonly an issue, or where you will have to apply this. Very rarely, or you can in theory also apply dropout already on the input layer. And then this is called dropout augmentation, which can help when you suspect that many of your features are correlated, right? What you're doing then, in a way, is you're kind of approximating something similar as what we were doing in random forests, where we said, well, for every split in every decision tree, right, we will not allow ourselves to check all the features as candidates to split on, but we will only select a random subset of features. This is quite comparable. For every mini batch, I will only update my weights based on a subset of features in that input layer, and I will ignore other features in my input layer. So it's very similar to what you saw there. Of course, what can also happen is that for a while, or it could be that your validation loss seems better than your training loss, because validation loss, again, is measured without dropout being applied, whereas with your train loss, you are applying dropout. So the problem is harder during training than it is during validation, but that's exactly what we kind of want, right? We want to find a model which weights are in the end more capable to generalize. So as long as our validation loss is good, right, and as long as this continues to decrease, you can continue to train as always, right? Rarely, but that's a topic, a little bit of a side topic, but sometimes dropout also gets applied during testing or during inference as well. So you don't turn off dropout when actually predicting on a new instance. You still keep dropout on when giving your model a new image, for instance, to predict on. And the reason why that is sometimes done is because this is one of the steps that you can utilize. You need to add in something to your loss function during training as well, in fact. But this is one of the things that can help you to get a particular form of a Bayesian neural network, is by applying test time dropout or inference time dropout. And the reason how it works is, imagine you have a network which job it is to predict the price of a house, right? And you keep dropout on during inference. And then you have a new house with its features, you feed that on the input side, and you ask your network to make a prediction. And you get a certain point prediction out of there. The house is 230,000 euros. Then you ask it the same instance again. Normally you would get the same answer, but now because you're applying dropout, every time you ask it again to predict on the same instance, you're dropping out a differently randomly sampled part of the network, so you get different predictions. Predictions that will probably be relatively close to one another, right, or very likely, but then you can utilize the distribution of these or over these predictions to give you some sort of uncertainty interval or prediction interval in that case. So not only do you get a point prediction, you also get some uncertainty quantification as well. There are other ways how you can do that with conformal neural networks and so on. This is one way by utilizing dropout. Right? And if you ask your model 20 times to predict the same instance, but the predictions are widely different, then probably you can kind of see, okay, my model probably doesn't feel all too confident here about the predictions that it's making. Weights, yeah. You could, but I don't think that that would be a great idea to do, because then probably the weights that you're not, or you would pick another random subset also in every mini batch. Oh, yeah, that's not really done, actually. Typically, you just put an L2 on all of the weights and you slap them in the loss function. What is sometimes done, however, is that you use different regularization strengths depending on the layer that you're in. Where you say, okay, in the fully connected layers, I'm going to regularize more strongly, so it will play a heavier role in the loss function than maybe in the first layers. That sometimes is done, yeah, so that you apply different alpha values depending on the layer that you're in. That is something that you can do, but not including a weight altogether, less so, right? Yeah, batch normalization then. So I already mentioned this is one of the reasons why we apply the scaling factor also when working in inference with and turning off dropout. Batch normalization, it comes from the notion of, okay, we know from this issue of exploding activation values that we saw last time, that if you start with a network that you would make 200 layers deep, and so it's basically a matrix multiplication 200 times after one another, and you do not initialize your weights correctly, so you would give them values that are too high, for instance, or not sampled correctly. And if you apply this matrix multiplication 200 steps after one another, at some point in layer number 100, right, whatever, you would observe that your activation values start to explode. And that leads to numerical instabilities, that leads to a crash during training, or where you need to start from scratch again. And indeed, if you monitor, or if you would monitor the values of the activations that you get in each epoch of training for all of your neurons, if you see that they're like, some of them are blowing up, it's typically not a very good sign. So, okay, one of the things that we can do is we can utilize better initialization. We also know that it's quite important in the case of a neural network for these weights to behave well, that we normalize our input data, right? Normalize or standardize, right? But that's something that we typically will have to do, and it's quite crucial. So if that is important for the input layer, why don't we also apply this kind of renormalization for all of the activations that we get after an intermediate layer as well? Why don't we on the fly normalize the outputs that we get from the activations of a hidden layer of units, basically? And that's the idea of batch normalization and also variants like layer normalization and things like that. It's basically, okay, once we get the output of activation values, we're going to renormalize them in these intermediate steps as well. So this will also help us to maybe keep the learning more stable and to maybe allow us to make our models deeper without the activations going haywire and things like that. Problem with this is that it is of course not so simple to execute for these intermediate layers than it is for the input layer, because the gradients that we get, they are based on the activations that we get in a mini batch of examples. Okay, we know that. So we assume that the activations will remain the same for each sample, and weight updates are calculated also under this assumption. But the weight update that follows changes depending on the inputs that we get in each layer, except for the very first one. So the problem is that if we play around with or if we rescale intermediate activations, then of course we are changing the values, and our weights or the way how we perform weight updates will not work anymore. So it's not like you can just take a mini batch of activation values and normalize them in some way. You would have to rescale them in some form, and you could take a look at, okay, what is the mean value of these activations, and I'm going to rescale them to bring them closer to 0. And then I update my weights, and then I give my next mini batch, and then that one doesn't work anymore because now I'm normalizing with an assumption that only was valuable for that mini batch. So basically what you need to learn is that if you would have, or what the problem boils down to, is you give mini batch 1 of examples, and you would take a look at the activation values that layer number 2 gives you. And here is the 0, and they look something like this. And you say, from there, I know, or I can see that we should apply normalization, where this distribution looks more normal again. Okay, fine, that's the case for mini batch 1. But who's to say that mini batch 2 follows the same distribution of activation values, and hence the rescaling that you did for this first mini batch still works for the second mini batch? Very likely you will end up in some kind of application where, what you are trying to do for the first mini batches is totally not the optimal choice in terms of rescaling for the following mini batches, let alone for what happens then in the layers afterwards. So you do need to be a little bit smart here in how you approach this, and this is why this took like a little bit of time to work out as well. So basically what this batch normalization paper implements is it tries to stabilize the distribution of the inputs to each layer to kind of learn actually how you should apply the normalization itself. What else? Some people also claim that applying batch normalization reduces overfitting as well. Maybe, maybe not, because it has a slight regularization effect, but that's never been strongly proven. In some early papers, they said, well, you can just forget about dropout altogether. If you use batch normalization heavily, you in fact do not need dropout. It's a bit of folklore going around this. Some people will, it basically means you should experiment and see how much dropout do you need, how much batch normalization do you need. What is the case, though, is that for every large language model that you see nowadays, all of them are still utilizing some form of intermediate normalization of the activation values that you get. In most cases, that is layer normalization, which basically applies a normalization not after every mini batch of examples, but after you have gone through the complete layer and then normalizes based on the activation values that you got there. Theoretically, you could also apply a normalization after having seen just one instance, so you do the normalization instance after instance, but that's of course a bit less stable, so that gets less commonly applied. In chaos, it is just basically importing the batch norm layer and importing the layer norm layer and just putting that on top of an activation layer, and then basically does it out of the box. What else? Data augmentation. Yeah, this is also a bit of a tricky one. Very early approach when people were trying to train networks from scratch, and especially in the image domain, And when facing the issue of, I here want to detect or I want to install a camera in my garden to detect whether there is a squirrel in my garden or not. I think this is a squirrel, I'm not really sure. But let's say that I want to do something that can detect the presence of this particular animal. And I've been hiding in my garden for a couple of days, and I've taken some example pictures of this animal so that I can teach my network, is it there or is it not there? I've also taken some pictures without the animal. That's probably easier, right? Because for the animal, I need to wait until it's there. So I have 1,000 pictures of my garden from different angles, and I only have a couple of pictures of this particular creature. We know that to train neural networks effectively, and especially CNNs, and especially if we make them larger, that with just 5 images, positive images, we're probably not going to get the expected results, especially not if we start training from scratch. So what's one way I could go back into my garden to take more pictures? That's the best actually that you can do, but it's raining outside and it's cold and I'm not in the mood to go outside anymore. So instead, what is commonly done is you apply some form of data augmentation. Data augmentation meaning that, okay, given the pictures that you do have, you try to apply slight transformations like flipping the image, rotating the image a little bit, and so on, to create a more varied set of images that you can then utilize to train your network with. Now, important here is this can, of course, also help to prevent overfitting because you're adding in more variety, right? Important here is most of these image augmentation libraries, they offer a whole bunch of clever ideas in terms of, hey, here is how you can augment your image. You can rotate them, you can shear them, you can play with the color spaces, you can blur your images, you can make them darker, you can make them sharper, you can apply these glitchy effects even to them, right? Some kind of image distortion effect. You have augmentation libraries that apply fog to an image and stuff like that as well. Can be useful. For instance, a couple of years ago, me and a colleague worked on a case where we classified naval ships from World War II for the Royal Navy in the UK. And there we utilized the fog image augmentation, for instance, because there you had images that were taken in more foggy conditions, so it makes sense to apply this augmentation on the images that are not in foggy conditions as well. Why does it make sense to apply a certain augmentation and not apply other augmentations? Okay, think about it for the situation where I'm in my garden. It's quite likely that I will also want my camera to be utilized when it's getting dark outside, right? So hence making those images darker probably makes sense. It's quite likely that sometimes there might be a bit of blur going on. It's quite likely that the animal will appear in front of the camera at an angle. So small rotations I can also apply. But no matter which day of the year it is, it's going to be very unlikely that suddenly I get like this squirrel from hell showing up with a red background, right? If that ever happens outside, I think the squirrel is the least of my issues, right? So does it really make sense that you augment your set of images and have the model learn on this? Not really. So make sure that your augmentations are in line with what you really expect your model to be confronted with at inference time, right? Then this can work well, but do not just apply this and go crazy and think that it will help. Your test set will not contain images that look like this, right? Meaning that you typically should also only augment on your train images only. Now, again, for everything in deep learning, there are exceptions. Sometimes people will also apply augmentations at prediction time as well. Why? Again, to get more stability in your predictions. Like, I give you this particular picture, and you're not quite sure that you see a squirrel again. The probability that you spit out is like 52%. Okay, let me make a couple of augmentations, give those as well. Again, ask for your predictions, and then maybe for some of them you see the squirrel a bit more clearly. Right, so I can average the predictions that I get. I'm again trying to get some range of certainty, just as what I did with dropout previously, but now I do that using augmentations. Now, this is also possible for text, audio. Implementations that try to make augmentations for text exist as well. Then you can think about, you have a sentence and you can try to replace some words with synonyms of those words, right? That would be an augmentation that you can apply on text. For audio, similarly, it's mainly done for images, however. Most popular library, it used to be the case that this was something that you did on the CPU and hence was pretty slow. And so in a lot of cases, people decided to first generate an augmented set of images beforehand, and then just incorporating those into the training loop of a model. If you take a look at the image data generator of TensorFlow and Keras, for instance, you will still see a lot of tutorials that use that one. Some libraries like Albumentations then came along, and FastAI also did this, and they said, well, maybe another way how you can apply this is by incorporating the augmentations, expressing why should that be something that we do on the CPU. Why can't we express an augmentation like a rotation of an image? Why can't we express that just directly as part of the neural network itself? So where the first layer, first you have your input layer, which was this width, height, and 3 channels because we had a color image. Instead of the first layer being those convolutional neural networks, why not have the first layer be a rotation augmentation layer, where we say, well, take this image and first, before you pass it to the rest of the network, rotate it a little bit, right? And then it's the GPU that can do this, and typically goes faster than having to do that on the CPU. Yeah. No, typically they all get the same importance. And typically the way, and especially if you work with these layers, what happens is that you go over your original pictures that you have, but every original picture gets augmented into a slightly different version of that original picture. Of course, if you apply no flipping, no rotation, no color change, you can end up with the same original picture. But typically you perform multiple epochs, again, of training, and for every original picture, through this you generate an augmented one. Yeah. So typically every original gets augmented into a bunch of variants, basically, is what happens. Yeah, you could try to set up weighting schemes where you say, but I will also pass my original pictures through, and I will give that a higher weight, for instance, in some way. You could do something like that, but again, rarely done in practice. Because if you really feel that it helps, then maybe your augmentations are not so good to begin with, right? And maybe you're augmenting too much. Then that's basically what you're seeing there. Yeah. If you would use the augmentation layers in Keras itself, so you put that or you make that part of the model, then also during test time, these augmentations will still be there. So also during test time, if you're running an original image through your network to predict on, it will perform an augmentation on that image. If you really don't want that, then you can basically take out the layers of that network, make a copy of the network so that you can start with the convolutional layers directly and not perform the augmentations. But if you go for an approach where you do the augmentations in the network itself, then they will also be there during test time. Augmentations, one way to do something with a small amount of data was very common. Nowadays, what's even more common is that you apply some sort of transfer learning, that you apply some sort of fine-tuning, so that you work with a model that's to some extent pre-trained, right? Where you take a model that someone has built already and you just try to see whether that works on your use case. And different instantiations of fine-tuning exist. For instance, what you could do is, let's say that you have a model that already predicts the 1,000 classes for ImageNet. What you could do is not change the weights of that model, which results in these 1,000 probabilities whatsoever, but just stack your own couple of dense layers on top of that to get a number of classes, for instance, only 3 classes on top of that. And you only fine-tune or you only train those weights, but you keep these weights fixed. That's typically called you freeze part of the network, because you freeze those weights, meaning that during training, you're not going to perform weight updates on those weights anymore, right? Same as what Dropout did. When we set the activation value of some neurons that we dropped out to 0, also we did not update their weights as well. But there it was different neurons per mini batch. Here it's a whole block of our network that we're keeping fixed. What else could you do? You could say, well, let me take out, like a surgeon, you step in and you take out this last layer of 1,000 neurons, because you don't have 1,000 classes, but you replace that with your own layer with only 3 neurons, right? And then you, of course, also need to train this layer, but the previous layers, all these convolutional filters, they can probably remain fixed. If you see that doesn't work so well and you would like, or you realize that probably what the original network has been trained on is quite different than the data set that you have, you can also decide to unfreeze some of these previous layers, which are very likely going to be convolutional layers, and also continue to train them a bit further as well. But probably the very first layers doesn't make sense to continue to train them, because these layers typically tend to learn very low-level features. They try to focus on edges and color blobs, and probably no matter the task that you will do, edges and color blobs will be important. So why continue to train those? That work has already basically been done, and you need to focus a bit more on upstream, higher-level features. Today even, well, it's basically pre-training to the max, because today it's also very often the case that we will start, or that we will try to look for some form of pre-trained multimodal, like a JAMA tree, for instance, or we buy an API key for OpenAI, and we will not do any weight updating anymore. And we will just ask that pre-trained model, what is this? Or we will utilize something like a SAM2 from Facebook, a Segment Anything 2 model, and we'll just ask it, well, given an image, right, cut this up into segments for me. Maybe then you can still add like a small model on top of that you still train yourself, but the amount of fine-tuning that we have to do is getting less and less, because we have these foundation models that basically can do everything already anyway, right? So it depends a bit on the route that you want to go for. An interesting kind of early example, but that shows this pretty well, is this one. Skip the tutorial. Yep. Yes, okay. So this illustration basically allows me to train 3 classes, right? It doesn't know which classes I will give it to, so I will first give it a couple of training examples. So for my first class, I'm going to use this thing. So this is my green class, as it's called here. And I'm going to give it a couple of examples. And I'm doing data augmentation, right? So I'm showing it different angles. Then as my second class, let's say this box of crayons. And this I'm not going to give from the top, because I will probably spill it over. And then the last class, I'm tempted to say something that looks different enough from this bottle, although it could be the same. It wouldn't do a bad job at all. Microphone, done. Yeah, they use cats as the output here, so ignore that. And now I can use the model, right? So now I can give it new images. So I look heavily like a microphone, or it's darting between microphone and crayon, but from the moment that I bring this in, you see that the green class shoots up, right? And from the moment that I bring in this box of crayons, you see that the purple class goes up. And from the moment that I bring this microphone in, it's red, right? So this is an early example. How does this are web browsers capable fast enough to train this on the fly, right? No, that's not what's happening here. Basically, the approach that's being taken here is extremely simple. And what they do is the following. Take a pre-trained SqueezeNet model. And SqueezeNet is a very small model that's capable to run in a web browser. So yes, you can have SqueezeNet make predictions, but it's pre-trained. SqueezeNet has been trained on ImageNet. So again, what it will spit out if you give it an image are 1,000 probabilities. When you as a user train, quote unquote, this model, for every image that you give it, all of these images that I consider to be my green cases, store this vector of 1,000 number in a small list. I don't have a lot of training examples here, so this list is not that large. For the orange cases, same thing. Ask this network, what is your prediction? Store it in this list. It's not that in the original ImageNet set of data, that box of crayons was one of the classes there, right? But I don't need to know that. Probably there is something, a representation, which is close enough to this box of crayons, and I'm only working with 3 classes anyway, so probably there will be a mapping that I can perform from this 1,000-dimensional prediction output that you give me to this new thing that I'm trying to learn. And then once this is finished, then the user gives us a new image and asks, okay, dear network, what is this? Again, we ask the network, please predict the 1,000 probabilities for this image that we're now looking at, that we get from the webcam, and do a k nearest neighbors comparison to these train vectors that we had stored using something like cosine distance, and then just based on the number of 5 nearest ones, we predict this probability that we get there, or the number of 10 nearest ones, or something like that. So it's basically a KNN model where we use as the features the predictions that we get from an already trained model. And this works relatively well, as you can see, right? It's fast, it's easy to train. And the key insight here is that we aren't changing any of the weights of this pre-trained SqueezeNet model. We're not learning anything new. We're not fine-tuning this thing in any way in this case, because that would not be possible to do in a web browser. Up until a few years ago, when they released version 2 of this thing, and then they are actually doing fine-tuning in the web browser, right? So then, by then, web browsers had become smart enough or fast enough to do this sort of thing. But in this version 1, it was basically a simple KNN lookup. What can you do with them? Image classification, for that, CNNs are actually quite okay, and they do a good job. It becomes a bit more tricky if you do not just have to detect that there is an object of a certain class in an image, but you also have to detect where the object is. And then you can start playing around by having a prediction head at the top that does not only predict what is in the image, but also tries to predict, let's say, the upper left and lower right coordinates of this thing as well. So you train it and you basically ask it to predict 4 extra numbers, 2 numbers corresponding with the x and the y of the top left, and 2 numbers corresponding with the x and the y of the bottom right. You can see that then this can get a little bit more tricky if you might have multiple such objects in an image. And there might be different classes that are mixed together in the same image. Then it becomes a little bit more cumbersome, and you have to think about kind of alternative architectures. Like the YOLO series of models, you only look once, and there is also a very recent new one in that space that has been proposed. They are capable to see multiple objects and draw bounding boxes around multiple objects in an image, but their architecture is more involved. What's also typically more cumbersome, and where you will also tend to utilize some pre-trained thing rather than trying to train that from scratch, is when you want to do what's called image segmentation. And image segmentation basically means that you have a class per pixel in the image. In this case, which pixel is part of the dog, which pixel is not part of the dog. And then you can draw, of course, a nice line around the dog itself, right? Or if you are a self-driving car, is this pixel a tree? Is this pixel a road? Is this pixel another car, right? They do something very similar in that case. Why is it hard to train? Because hardware can't do it? No, nowadays it would be okay, mainly because you need the data. And labeling data where you can label every pixel, it's quite a lot of work to do that, right? That's also why these self-driving car companies and so on, they're paying huge amounts of people to do nothing else than data labeling the whole day, right? To train these models on. So that tends to be a bit more cumbersome. If you would be interested in knowing like what is utilized for this segmentation kind of approach, very commonly there still today in diffusion models you also find this, this architecture, is the U-Net architecture. The reason why is because it looks a little bit like a funnel shape, like a U-shape, where you have a encoder part where you first basically utilize standard CNN layers to take an input image and convolve that down to an intermediate representation. And then you apply deconvolutions where you go from this intermediate representation to an output image again. Why an output image? Well, now because for every pixel you want to predict a class. So if you have 10 classes, then your output image will be width times height times 10, because for every class you have basically an output channel that you want to get there. So it's an encoder-decoder setup. Standard U-Nets also have skip connections between the encoder part and the decoder part. They also apply forms like pixel shuffling to have this work a little bit better. That's also a little bit more advanced. Details not so important there. But if you would like to apply image segmentation, the U-Net architecture is something that you will see quite a lot. And this is maybe a better representation for why it looks like a U-Net, right? So the letter U. So you start with an input image. Basically, you apply standard convolutional operations here. So this is a standard conv 3x3 with a value activation. You have some max pooling that goes on to reduce the image size, as we saw previously. And then on the other side, you are basically performing up convolutions, and you're basically going back to an output segmentation map. In this case, the reason why this does not have the same width and height as the input image is perhaps here we don't really need a class per pixel in the original image, but maybe 2 by 2 squares of pixels are okay as well. So it's not that the output size necessarily needs to be the same as the input size, depending on the granularity of that heat map that you're basically trying to predict. These are residual connections that are also connecting the encoder part and the decoder part, because here too, these residual connections, they help with the vanishing gradient problem. If you would not have those, then basically this whole stack of layers that we have here is already quite deep and very hard for gradients to flow from here to there. That's what basically this residual connection helps us with. YOLO is something that I already mentioned. So basically they combine two architectures. So first of all is they have, or they apply kind of a slicing of images. You can call this like a very early implementation of patches, something that vision transformer models actually also rediscovered. So here the idea is that you first slice up your image in a grid, and you utilize something like a UNet, again in this case, to predict class probabilities per block in this image, right? So here basically you try to learn some form of segmentation that can say, well, does this block here, does this contain a bicycle, or does this contain a dog, or maybe it contains both, but then one of the probabilities will win out, right? So we can then color, if you will, these patches that you have based on the class probability map that I get from this UNet architecture. And then a separate thing, or a separate part of my architecture can learn what the bounding boxes should be. So this basically learns a stack of bounding boxes where I do not really want to teach it which particular class that you are, right? That's the job of this lower network or this lower part of the architecture to do. But this top thing basically needs to predict where are objects and how are they surrounded by bounding boxes. So here the learning task is to draw bounding boxes in this image that are in line with what the ground truth tells you that they should look like, right? So you also should have a labeled set, in this case, of bounding boxes that you have for your images. And then the idea is that you have sufficient confidence in the fact that there should be a bounding box here. Well, keep that bounding box then, right? So the probability that this is a bounding box over here is high. Well, then keep it. What should the class be? What is the thing in this bounding box? Well, you can do that based on these predictions that you're making. If you see that 6 squares in this bounding box are all blue, well, then probably this is going to be a blue thing inside of there. So it's going to be a dog that's surrounded in this bounding box. And here we have a bounding box that goes kind of like this over here. The majority of the pixels, or the cells, I should say, because they don't necessarily map to exact pixels, the majority of the grid cells in this bounding box are yellow, so this is probably going to be a yellow thing that I can show there. And this small thing here, well, it's fully pink, so this is going to be a pink class, which is car in this case. So that's how this architecture is set up. To utilize as the loss metric for the bounding boxes, for this is pretty easy. Here you can have a ground truth, and someone has already labeled for each grid cell in the image what it contains, right? What can you, so there the loss function is probably simply like categorical cross entropy that you can utilize because you're predicting classes for each grid cell. How can you set up a loss metric for a bounding box? Well, there typically the intersection over the union is utilized, because if your ground truth bounding box says, well, you have an image and one of the bounding boxes is over here, right? Well, if you predict, I have a bounding box in the full image, well, of course it will contain your bounding box of interest, but those are easy predictions to make, right? If you always make a bounding box that spans over the whole image, yeah, you will have all the bounding boxes, right? Vice versa, what you also don't want is where your bounding boxes that you predict are becoming extremely tiny, because then you're also kind of missing the point. So typically what is done instead is, well, the idea is that the bounding box that you predict, one concern is I would like it to be of the same size as the ground truth bounding box. And secondarily, I would like it to overlap the ground truth bounding box as much as possible, obviously. So what I can do is I can take the intersection. So let's say this is my predicted bounding box. I can take the intersection of this bounding box and put that at the top of my fraction, and I can take the union, which is the ground truth and the predicted bounding box together, and put that in the bottom, and then I get like a nice trade-off between, are you not too large, are you not too small, do you intersect well enough or not, and a perfect bounding box in this case will have the same intersection as the union, so then you get like the same value, so a 1 as an output. So you can subtract 1 if you would like to bring that loss to 0 if you really have to, but doesn't really matter. In any case, you're bringing the loss lower. What that exact value is not really important. So then you get models like our early attempts where you can like find bounding boxes of cars, or this YOLO model that I already mentioned, or models such as BodyPix. They're all based on kind of similar backbone architectures. So all of these are based on, or at least the two right ones, they utilize a UNet architecture inside of them to help them make their predictions. This you shouldn't really do, but this is more kind of to show like if you really get stuck sometimes, again, you can get creative with how you utilize models like these. Let's say that your task could be, okay, we have taken drone pictures here, and your job is, and these drone pictures are from high in the sky, they might have been taken at different altitudes, right? Your job is to predict whether in a drone picture you can see the presence of a water tower. And we're not just interested in recognizing that there is a water tower, yes or no. We also want you to draw bounding boxes around these water towers. And it can be that there are pictures with 0 water towers, and it can be that there are pictures with multiple water towers in them. And you are thinking, okay, we saw that maybe I should use something pre-trained, or I could utilize something like this UNet thing, or I could try to fine-tune YOLO, which are all good ideas, and nowadays are not so hard anymore. But let's say, okay, my architecture is not so fancy to begin with, or my hardware is not so fancy to begin with, rather. What can I do? Well, what you can still do is you know how to train a small image classifier using a CNN. So what you can do, given all the pictures that you have, first take random small rectangles from these pictures. So sample random small rectangles from your picture and utilize them, given that you know where the water towers are. You can label these small rectangles as being, yes, you contain a piece of a water tower, or no, you don't contain any water tower at all, right? Because your rectangles are probably sometimes going to be smaller or partially contain a water tower because you're randomly sampling them. So just make sure that you have a good mix between positives and negatives again in your small rectangles that you sampled. Benefit, because you're sampling small rectangles, your architecture probably will not be so heavily or compute heavy to train on. Smaller images, always easier to train your network with. So you train this thing, and then during inference time, of course, you still want to locate the water tower, and at inference time you're working with a full large picture again. But then what you could do is, okay, just go over your image by creating this kind of sliding window where you start with the first small rectangle and then you move a pixel to the right or a couple of pixels to the right, and you continue to ask your network, what do you think? In this small rectangle, do you think that there is a water tower, yes or no? And this you can then utilize to create some sort of heat map where you will see, well, every time I'm sampling or I went over this spot, well, here is where my network said yes with a high probability. And then you can overlay this as a heat map, and then you can draw this as a bounding box, and then you get something with just a simple mini classification model. You can still do localization of objects as well. Today, like I said, this kind of heat map sliding-based approach would be maybe a bit too cumbersome because it's easy enough to utilize a pre-trained model and fine-tune that. But goes to show that even with sometimes the things you know, you can try to reinvent something that works for your use case. We saw two-dimensional convolutional neural networks, and the reason why we call them two-dimensional is because they generate two-dimensional output convolutions. Now the question is then, does there also exist something like a one-dimensional CNN or a three-dimensional CNN? And indeed, yes. So a one-dimensional CNN, that commonly is applied when you're working with text sequences. And just as for an image, we said we start with something that has a width, a height, and a certain depth. With text, we just have a certain width, right? The tokens of my text, or maybe the words, this is a, and so on. And every letter is represented as a one-hot encoded vector. Then my depth is as many characters that I have in my vocabulary, in this case. 26 plus dot, period, commas, whatever, right? So my depth is probably going to be maybe around 50. And I have a width, which is equal to the number of characters in my sentence. What's a convolutional unit going to do in this case? Remember the way how a kernel gets defined. Now for my kernel size, I will not say you need to be a 3 by 3. For my kernel size, now I have a one-dimensional CNN. For my kernel size, I'm just going to say, well, I have a kernel with size 3. And likewise, it's going to apply the same operation by sliding now from left to right over this input. It's going to multiply each kernel weight, or kernel weights, because my kernel will have a depth of 50 as well, multiplying it with the vector that it receives, summing everything together, and generating an output value at this step. Right? And again, the output now will be itself not a two-dimensional map anymore, or two-dimensional image anymore, but a one-dimensional convoluted output. And you can stack neurons then in the same way on top of each other, or layers of these CNNs as we did previously. Sometimes used for text analysis, sometimes used for time series analysis, because you can also set this up in for time series prediction tasks. There are other variants as well, like capsule networks and so on. One of the issues with, if you look at how these two-dimensional CNNs work, is you might have filters that are good at spotting the presence, or that become excited when they see an eye in a face, and you might have another filter that becomes excited when it sees the edges of a face, and you have another one that becomes excited when it sees a mouth or a nose. Yeah, if you have a bunch of filters in layer number 5 that like to see these things, then layer number 6 will be able to pick up on those and say, this is probably a face. But very likely, if you have a network that you have trained on a whole bunch of faces to detect, I see a face, yes or no, and you would construct like some sort of artificial image that looks like this, it will also see a face. It's also going to get excited by the eye being here and the nose and the mouth and so on. It's hard for these upstream filters to learn. Yeah, but they should also be in some hierarchical, spatial, coherent form with one another, right? And if you look about how these stacks are set up, it's maybe a little bit logical that this hierarchy, or this composition, if you will, in the image is hard for them to learn. Will you ever see a face like this at inference time? Also probably not. So that's why maybe in practice this is not that big of a deal, right? But it's kind of, you could say that this is a drawback of these standard architectures that utilize CNNs. Ways have been tried to, or like things like capsule networks have been proposed to do this a bit better, but didn't really take off. Another thing that you typically see is that for us humans, if you would see these 5 pictures, for us it's very easy to immediately recognize all these 5 pictures are the same thing. This is all the Statue of Liberty, right? Because we have evolved, or our visual cortex has mainly evolved to be primarily well suited to recognize silhouettes of things, right? No matter whether it's light or it's dark, and the reason being that if you're living in a cave and there is a tiger with long teeth running towards you, even in the dark, you would like to see the silhouette of those teeth correctly so that you can run away, right? So a lot of animals are evolved to be good at doing this. Not all of them, right? But we, for instance, are. If you'd inspect a CNN network, and if you would have examples of different lighting conditions such as this one, you might end up with a network which is capable to predict for all 5 of them, you're the Statue of Liberty. But if you look at the series of units that get excited, so that activate heavily in order to establish this final prediction, it's probably going to be a different set of neurons for this image than it is for this image. Even already at the first layers. Because here you will have neurons that get excited by black edges being present, and here you will have neurons that perhaps look at different sort of edges. Right? So this edge is not the same as this edge for these kernels that we have. Right? Now, you could say also here too, aren't there ways how you can mitigate this? Maybe you can first, you could think, or you could question whether it would not be possible to, instead of only feeding the color image to your network, that you first also create black and white versions, or where you manually already apply a Sobel filter to maybe threshold the image in a certain way, and then you can have some filters in your network that are focusing more heavily on silhouettes. Yes, sure, you can do all of these things, but the whole goal of this approach of deep learning is that we don't want to do too much of this manual pre-processing ourselves, and we would like to have the network learn all of this stuff. Similarly, if you think about even the most simple case, if you remember the visualization from last time, if we have an input image And remember that we drew the letter 3 in there, or I think it was 3 anyway. And we inspected the filters in the first layer. We saw that if we looked at our two-dimensional output maps, that for some of them, they got heavily excited by like these downward edges. And for another filter, it got heavily excited by like side edges, for instance. That also means that if you would now say, hey, let's rotate this input image, right, so that it looks like a sideways tree, that for this network, you would have a complete different set of outputs. It would be different filters that get activated for these parts in the image, might fail to see a tree there as a result, because it didn't see sideways trees in its training data. If you do that and you augment your images in this way, then of course your network would be capable to learn this, but probably again by utilizing redundant pathways, not by the same filter seeing both an upside down tree and a sideways tree. Right? You probably have two filters that would need to learn this in a later part of the network. And again, you have versions of CNNs where you not just learn the kernel that you slide over from top to bottom over your input image like we did previously, but you also have more adaptive variants where here kind of a choice which is still fixed is as an end user we can say I want you to learn a 3x3 kernel, but no matter the position in the input image that we are at, right, to convolve our output from, we are just taking the same 3x3 neighborhood around that pixel to multiply and sum, or to take the sum of products of. You could think about, yeah, but couldn't it be the case that depending on the pixel that you're currently flying over, that maybe you also want to change the neighborhood of your kernel and maybe look at a wider range or a shorter range, or maybe also learn how to rotate this kernel depending on where you are in the image. You can make all of these things learnable, right? If you know a way to express them in a forward operation by a set of parameters, right, and a set of inputs, you can learn to express or to do anything with these kind of things. But again, the question is a little bit, do you have enough data then to train it with? Is it worthwhile at the end? Is it feasible to train it? Because you're introducing more parameters at the end of the day. Here we had a simple 3x3 kernel, so 9 weights. Now you also need to learn how to offset all of these kernel positions, or maybe how to rotate them around and so on. Based on what you're currently looking at, you're making the task already a bit harder. But ideas like making convolutional networks shift invariant play with that sort of stuff, right? So that exists. Yeah, this is the texture thing again in practice. So what this paper tried out is, again, a pre-trained network. Indian elephant and tabby cat are two of the classes of ImageNet. Yeah, why? Because they choose those to be two classes from these 1,000. If you give a pre-trained network a close-up of this, then it will be very convinced that it's an Indian elephant. If you give it a picture of this cat, it will be also very convinced that this is a tabby cat. Now, for us, quite likely we have an easier time seeing that there is a cat in this image than immediately seeing that there is an Indian elephant in this image, right? For us, again, we look at shape, we look at silhouette, like texture is also important, but this could also be another animal, right? I'm not very convinced here. So then you can kind of question, okay, what if you combine this cat with this texture in this way? Will the network then think that this is a cat, or will the network think that it's an Indian elephant? And it thinks it's an Indian elephant also in this case. So again, it's focusing more on presence of texture than it's focusing on presence of edges. For most humans, if you would take a child, I would not show them like the text here, but just show them this image and ask them, what do you see? They will say a cat, right? They won't say an Indian elephant in that case. But okay, is this a problem? Not really, but just, yeah, give some interesting insights into the way how these networks behave. Newer architectures, they have also switched from using convolutional approaches, as we saw, towards more transformer-oriented approaches. Basically, this boils down to, we still need to discuss the transformer architecture later when we talk about text, but here the idea is, why don't we apply self-attention mechanisms to images as well? A problem, text is a sequence of letters. For an image, if you would like to, or if you need to attend to the whole image, that's a little bit computationally heavy. So it might be better that we also try to represent our image as a sequence of smaller things. How do you take an image and represent it as a sequence of smaller things? Well, you just slice up your image into patches, again, into small pieces, and you make a sequence out of small pieces, and you use that as your input sequence for your transformer model. Then you get like an attention network or a vision transformer network. But then some people have questioned like, hey, but is it then really the transformer mechanism that works here, or is it more the fact that you first cut up your images into smaller pieces that is kind of doing the main lifting here? And then you had papers such as Patches or All You Need that kind of question this idea of transfer or self-attention being necessary in the first place, which adopts yet another kind of architecture which seems to work very well, which is called ConvMixer. And if you check out the Keras tutorials, they show you how to implement this architecture for images, should you want to try that one out and seeing how well it does on your data set. So this is itself kind of a follow-up from MLP Mixer as well, but this is kind of the, currently we are like in this situation in terms of what people have done with images. An interesting kind of showcase of this, SOTA image classification. If you look at over the years, what we have seen from 2012 up until today for standard image classification on ImageNet, going from AlexNet to VGG, the jump there was pretty dramatic. From VGG to ResNet, the jump was pretty dramatic. EfficientNet, those are models that you can find pre-trained versions of in the Keras repository and use them directly. Accuracy of top one accuracy of 86%. Since then, we have seen some improvements, but we have kind of plateaued off, right? And here you find like models which are like more vision transformer based, for instance, but where you could kind of question if EfficientNet already does the job relatively well. How important is it to then still, for these 1 percentage points, switch to architectures which are drastically more heavy? For standard image classification tasks on a data set that you have, perhaps not so much, right? Now, of course, obviously, the other kind of step here is that these foundation models that are being introduced that have just been trained on all of the images that they found on the internet and that you just utilize that. Okay, I think we can go for a break. By the way, if you would be interested for the assignment, one of these pre-trained foundation models for images, or I already mentioned this, but here you can see it in practice, is called SAM2, Segment Anything 2. And it basically, it's capable to segment on every sort of image that you give it. And also video frames, it does a good job. And then basically starting from this segmentation, their idea of fine-tuning is that you then put a small model on top of this segmentation map to help you predict, well, what do I have here in terms of an object, right? So again, you could try playing with this. It's not hard to set this up. This is well-written code, basically, easy to install and utilize. So again, feel free to utilize that if you want to play around with this. Good. Adversarial attacks, but first we will go for a 15-minute break. Okay, let's continue. Couple of additional closing statements. First of all, about adversarial attacks. So this is also something that has been, or is kind of an illustration that these networks are not always perfect. Question here is, and you have all seen, I mean, it's the same issue with hallucinations as well in some sense, but the idea here, or the basic premise is, let's say that you have a certain picture. You ask a network that you have trained, what is this picture? Okay, panda as the highest predicted probability, correct. And then we can ask ourselves the question, is there a way how we can modify this input picture in such a way that I can drastically have my network predict something completely different? And obviously the interesting part is then, what is the minimal amount of changes that I then have to make to this image in order to sway the prediction of my network? And it turns out that the amount of changes that you need to make to change this panda into a gibbon, according to this pre-trained neural network, to us, we don't see a lot of differences between these two images. It's not that the right-hand image for us is not a panda anymore. So yeah, is this an issue? You might think, yeah, but of course, this is a deliberate attack in the sense that this is really someone having the freedom to take this pre-trained network and kind of optimize an adaptation or some change to make to this particular input image to have the network change its prediction around. But people have been investigating ways how to make networks more robust against these attacks. How do we do that? Well, actually, we can utilize stochastic gradient descent as well for this, or you can utilize, again, any optimization technique that you want to utilize. If you think about it, what now is my, or what are my parameters? Well, I have a certain input image that I started from, this panda over here. I have my pre-trained neural network, which is basically, well, just take an input image and predict me. Let's say that we extract from here what's the probability of you being a panda. And then I have some, or my task is given some noise that I'm going to add or subtract from this picture that I have to start with. The pixels in this image, the noise that I'm going to add, those are now basically my parameters, my weights, if you will, that I can optimize. And my loss function probably will boil down to, well, first of all, the closer that you are, or the closer that you are to your original probability of panda, right, the worse. So probably my loss will incorporate some aspect in terms of, well, maybe the inverse distance of the predicted probability of image plus noise compared to the original probability that I have. So maybe if these two are very close to one another, then my loss is very high. So I could express this maybe as 1 over the distance, or this first probability minus the second probability plus a small constant, so that this does not become 0, something like that. Of course, this makes it easy, because what I can do, or what I could figure out, is probably my optimizer is very quickly going to find that, yeah, if you make everything completely black in this noisy image, and you put that over your panda that you had, that your panda is not there anymore, and of course the network is going to change its prediction. So another loss component that we're probably going to add in is probably again going to be something like, well, an L2 loss component that says, well, but the pixels that you put here in this noise map that you will apply, they can only be very small changes that you make, right? So keep the amount of changes that you make as small as possible. And then what small means for you, you can again express that in different ways, where you say, well, we could either change a lot of pixels a little bit, or you could change very few pixels, but maybe we are free to change them a lot, right? So you can also, or there have also been investigations that kind of say, or try to investigate, maybe there is, no, that's out of here, but there was a paper that investigates if in a picture like this, what if you can only change 1 pixel? Is it then possible to find an attack that still works? And indeed turns out that an investigation that they did, that was indeed possible. Will be more noticeable to a user because the user will see, strange, why is there a bright pink pixel in the middle of this image? But still, you wouldn't expect that this would completely change the prediction of a neural network around. Now you could say, well, the thing, of course, that you're lucky about is that you kind of are free to query this kind of pre-trained network that you have with any sort of image. If you have access to the weights of this network, then it will probably be even easier to do so. But if this is a model which is exposed as an API and which is not so easy to query, maybe that will already be a little bit more difficult. Well, turns out that there exist different forms of this adversarial attacks that have been investigated over the past years, such as, turns out that you can also steer a model to do certain things based on the order that you presented the input data with during training. Can you think of ways such as maybe you're an adversarial developer and you're afraid that your company might fire you later, and you're working for OpenAI? Would it be possible to poison the training data in such a way that maybe later on you can have the network do certain things depending on what you feed in the input data? And again, this concept of radioactive data is also possible. There is a fun tutorial on hacking neural networks that goes over these different things, backdooring, buffer overflows, and so on, which is pretty fun to play around with and to kind of show like which types of attacks that you could come up with in a practical context. And of course, we have seen attacks with like stickers on stop signs and things like that. This is an example of where someone poisons a face recognition model with particularly crafted images where they trigger using a certain glasses, and then when the user wears these glasses, indeed they're capable to show that the model is not seeing the correct person anymore. So if you have access in development of a model, of course there is even more stuff that you can do there. Another thing to briefly discuss is going back to the concept of interpretability and kind of investigating which concepts now still work, which model agnostic approaches, for instance, or which model specific approaches that we can come up with when we are working with vision models like these. And this is not new. I think maybe already saw this previously, but this is the article from Byte magazine from the 80s, where first self-driving car, a very simple multi-layer perceptron network with only one hidden layer or a couple of hidden layers, but already then researchers were asking the question, well, what are these hidden units actually doing? What are they looking at, right? And similar question exists today. And if you have millions of parameters rather than thousands of parameters, this question becomes maybe even harder. For a CNN, we already saw in this visualization that we can inspect the output maps, the convoluted outputs of filters of a neural network in the first layer, and that at least there it was relatively easy to see, these guys, they are looking at edges, these guys are looking at sideways edges and so on. But then for the layers afterwards, because they combine all the, or they look over the stack of all the generated convolutions of the previous layer, that already becomes then a little bit harder to then kind of see, okay, what are these filters actually doing? So maybe we can uncover this, or we can open up that black box a little bit further. Very early attempts. At some point, this goes to show that already in the early days of AI, people were trying to figure out things such as these. Hinton diagrams, where this works for a simple multi-layer perceptron. So here we have two hidden layers, and in each hidden layer we look at the weights of that layer, or we look at the weights of a unit, and then we use kind of colored blocks like these to indicate, okay, from my input layer where my neurons correspond with the different features that I have, going to a certain hidden neuron that I have there, can I visualize the weights like these? And as long as you do not have too many hidden layers and you do not have too many hidden neurons, then maybe you can hope that you can get some interpretability from this. It's basically inspecting the coefficients, if you will, but this blows up, or this would start to fail once you start to work with millions of parameters, obviously. So we don't use this, and nowadays we would say, well, what you really probably try to understand by doing this is, how do the different features that you have, how do they impact your outcomes? And for that, we already saw something previously that would work way better in this case. If you just have a tabular data set like here, and you're using an MLP, nothing stops you from also using Shapley values in that case, right? So that's kind of the takeaway for tabular data. Just also, like we did for XGBoost, and like we did for LightGBM and Random Forest, also there, Shapley values are probably the way to go. And likewise, with older techniques, such as rule extraction algorithms, they also try to do something similar, where you have a neural network, but you consider that kind of as a black box, and then you're trying to use this neural network to label a couple or generate a couple of additional instances, and then you go, it's basically the global surrogate model again, let me build a simple decision tree then that I can kind of use to get some insight in how this black box neural network is working, but I do that by means of this simpler decision tree that I'm building. So as some examples, so this is decompositional rule extraction. Don't worry too much about this. This is not utilized anymore. This is again to show kind of what people were doing in early examples. So the idea is, okay, you have one hidden layer. you start with your basic inputs that you have. You have your response, a binary target in this case. In this layer, one hidden layer, you have 3 hidden units. Feed those instances through that hidden layer and keep track of the activations that you get. And then you apply some form of clustering technique that clusters the activations for these 3 units into distinct groups. And then on top of that, you try to apply a rule mining algorithm that first tries to learn based on the inputs, which cluster label do you get here, and then based on which cluster label do you get there, which response do you get, and then by merging these 2 sets of rules together, you can get rules such as if age is higher than 34 and income is 1,500, and the response is a yes. So you kind of inspect the activations of your neural network to maybe whitewash it a little bit like this. Again, not really worthwhile, just use Shapley values, way easier, will work way better. This is the idea where you utilize your neural network to generate a couple of additional or to label your instances. So you look at the predictions of your network, and then you use that to train a decision tree model from that, and maybe then you use your neural network to generate some additional instances in the leaf nodes as well. Again, you try to approximate what your neural network is doing by means of a simple model. Again, this is not really that modern anymore, just use Shapley values. 2-stage models, this is kind of a form of boosting where you say, and actually this is not that dumb, especially for tabular use cases, you could say, well, maybe in my context, I really, for the majority or the bulk of the work, I need to use something which is highly explainable, like a logistic regression model. That model still makes a certain amount of errors. Then I'm going to boost on these residuals by means of a neural network. Again, this is not neural network specific. This could be a LightGBM model for all we know, right? You're basically also boosting on the residuals, but here you're starting deliberately from a model that is highly explainable for some reason, because your context needs that or whatever. So for all of these cases, we can basically, if you have normal features, tabular features, the answer here is still basically just use Shapley values. And what about CNN models? So what about if you work with vision? Then maybe it's a little bit more complicated. So we already saw that we can look at the activations that we get. So looking at the convoluted output map. So here we have 4x4 filters in this layer and in this layer and in this layer, right? So we have 16 units per layer. We can take a look at the convolutions that a unit gives me in the first layer, and there I can still see you're probably getting excited by edges being there, right, as we saw previously. But then to construct an output map of a unit in a later afterwards, this is basically sliding its kernel over the full stack of 16 previous outputs that it got. So it's already harder to, I mean, it's also localized, but what does it really mean that you have like a white blob over here? You get excited by something probably which is probably present in these 16 images over there, but we don't really know what there anymore. So again, and especially if you use ReLU, as you go further and further in the network, these outputs will also become sparser and sparser, because ultimately this is trying to construct something where at the very end you get something that allows you to linearly separate your classes by then connecting them to a fully connected layer, or by first doing a global average pooling and then connecting them to a fully connected layer. So this becomes harder and harder. Well, at least this becomes interpretable, because you will see, yeah, there is some linear separation probably that becomes possible. I could look at this output for an image belonging to class 1 and an image belonging at class 2, and I would probably be able to see that I get some linear separation there, but I'm not really understanding, but what is it that my network is looking at? What does it get excited by in this input image that I can't see by looking at these activations? And likewise, I could take the kernel for one of these filters, right? And I know that that is a 3x3 by, in this case, for instance, 16, because it has a 16 depth in the input. I could visualize again the weights of the kernels that I have here in some way, but these are basically just 3x3 by D matrices. That's also not really going to teach me or tell me anything. What is more interesting and more revealing is a very simple approach. And a very simple approach is that of maximally exciting inputs. If I have an input in here, and I'm trying to kind of understand, so for here, the question that I basically answered is, you're probably a unit that likes to see, or that gets heavily excited by, edges, left edges. I would like to answer the same question for a unit somewhere later in my stack of layers. What do you like to see, right? Well, what I could do is I could take my train set of images, I could feed them all throughout my network, I could step in one of the middle layers over here, pick a particular filter like this one, and just take the sum of the pixel values that I have there and use that as a proxy for, or use that as a measure for excitement, and then just check, okay, for you, dear filter in layer number 5 of my network, what were the 4 images that excited you the most? And this is already a bit more revealing, because at least here we have a better idea of what does this filter like to see, right? 100% yet? Not yet. I would say, well, it probably likes to see the color red, but maybe it likes to see a black blob surrounded by red. So it's not 100% clear yet, like what it is looking at, but at least this is telling me something more, right? At least I can group my images based on this excitement. What we can then also do is I can, and this is again a little bit more technical, so the maximally exciting images are the ones that you see in this and in this and in this frame of this image. You also see that there are heat maps associated there as well. So how do these heat maps work? Well, I know that to construct, for instance, in layer number 3, I'm starting with an input which is W times H times 3. That was my input image, which is a color image. Then I'm deciding the number of units in my first layer, and looking at the output example that I see there, I probably have 9 filters in this first layer. So these are going to generate me a stack of images if I would convolve through all of these filters, which are W times H times 9, because I get a 2-dimensional map for each of these. So I have 9 of these maps. Then I have another layer where I have 4 by 4 filters, so 16. So this is going to output me W times H times 16. And then my last layer is a 3 by 4, so that's 12. In this case, W times H times 12. What I can do is I now take for one of these filters in layer 3, let's say, how does it construct its input? Well, it does so, in this layer at least, by, it will slide its kernel over all the 16 images over there. And the way how these 16 output maps were created was by sliding the respective filter over all the 9 images in there. And these images here also, every unit created its 2D output map by sliding its kernel over the input image that I had there, and also over the full depth that I had there. Now some parts, if I would then look at what is the internal convoluted output that I get here, I would probably get something, right, that's pretty similar to this image, for instance. So that's the convolved output that this unit creates. So one thing I can do based on that is I can pass all my images that I have over this network, inspect what this particular filter in layer number 3 is putting in its convolved output, and I can say, well, the more white that shows up in here, the more brighter that this thing is, the more that you got excited by this input image. And then I just show for every filter the 3 by 3 images that excited you the most. And then what you can indeed start to see is that in the first layer, if I look at the top exciting images for these 9 guys, well, this one loves to see green. And this one loves to see diagonal edges. And this one loves to see orange, reddish colors. And then the next layer, there they already start to combine these basic shapes into more global patterns, right? This one really loves yellow. This one already starts to see like horizontal lines, like book lines and things like that. And then the layer further, well, here you see that these basic shapes are being combined into, here it's the shape of a grid. Well, here we typically, or we clearly see a unit that loves to see car wheels, for instance. Here we see a unit that loves to see, well, this is pumpkins or tomatoes or something like that. So we can keep track of the most exciting images, just as what we did in the slide previously. But if I then really want to know, but what was now the part of the image? I know that those are the 9 images that got you excited, but what was the part of the image that made you excited? In other words, if I take this convolved output, all the areas which are black, right, I know that they result from something where after I pass them into my ReLU activation function, all the pixels which are black are basically those parts, those pieces that didn't make you excited. So what I can do is working my way backwards from here. Every part that is black, I can basically take out of the convolved output maps that you guys created, because they didn't establish any output in my convolved. I don't need it. I can also basically wipe it out there as well. And then because I wiped up stuff here, I can do the same operation. Every piece which is black here, or which is 0 effectively, right? That's what I'm saying with this. Every output pixel which is a 0, I can also wipe out from here. And I can do that until I end up in my input image. And basically what I'm doing there is I'm saying, well, remove everything from this input image that we didn't need to construct the convolved output for this particular unit, right? And that's why you see that these maps here, they have a gray background, because if you normalize an input image so that all your values are between 0 and 1, what's the average, right? 0.5, that's going to be gray. So wiping out or removing in this case basically means, well, if we set this back to the average, that's how you basically can throw away the information but still get the same convolved output image. And then basically the parts which are not gray, this represents like this was the part of the input image that you need to retain, that you need to keep to get the same convolved output here in this filter. So then you know the part what made or what caused this filter to get or to create its particular output. And then this already starts or shows a better interpretable heat map of which parts in the image are important. What you can also do, just as what we did with an adversarial attack just now, we could also take it as an optimization problem. And we could say, well, what if, again, I start with an image that consists of random noise. I keep track of your level of excitement over here, and then basically through some process of optimization, that could be SGD again, change this image step by step so that you become more and more excited, right? But again, if you do that, you quickly end up into a region of extreme behavior of overfitting, where the image that you generate here, yes, it will make this unit super excited, but it will look like a complete mess, right? A complete glitchy mess, not something that's interpretable for us. So what we want to say is, okay, on the one hand, we want to generate an image which makes you as excited as possible, but preferably an image that looks like something that is also in our training data. We don't want to extrapolate outside of our training data because, yes, outside of the realm of real images, there are probably a lot of them that make you super excited, but then that's basically just because we have extrapolated or we're kind of in a region or a regime of overfitting. So typically, when we optimize this image that makes you as excited as possible, one component in my loss function will be, how excited are you, right? Excitement basically means we take the sum of the absolute values of all of these pixels, right? And then the higher that this is, the better. So in my loss function, I slap a minus in front of that. So minus excitement. The more excited that you are, the better, right? But we don't want to end up in a solution for this image that's completely crazy and nonsensical. So probably we also add in some form of continuity loss. And continuity loss basically means it's a loss that for every pixel in this image that we are generating, checks the neighbors and basically punishes on how different are you from your neighbors. Because most photos that we take in real life, there is some local coherence. It's not that you go suddenly from a bright pink pixel to a complete yellowish pixel. If I would take a picture here, this seat or this front row of seats, they're all kind of brownish, right? They don't suddenly switch and switch again and switch again. Yes, at the edges that happens. I mean, not that the whole image is gray, but like generally speaking, images are pretty coherent. Second, what I can also add to this is simply, again, our friend L2, where we say do not make super crazy values for these input pixels in this case, right? L2 normally you do on the weights, you do on the parameters, but here the parameters are effectively the pixels in my image, right? That's now what I'm optimizing. I'm not training weights of a model. My model is trained already. I'm training an image. I'm creating an image, right? So that's another thing that you can add in. And then you can say, okay, pick a filter in your network, apply this optimization, and please find me an image that we generate from scratch that excites you as much as possible. And indeed, for units in the first layers of a network, they get excited by images such as these. That's what they dream of, that's what they love to see. Yeah, edges and simple shapes. But then if you go higher up in the network, you do see that indeed there are images that love to see flowers, right, for instance. So this is called feature visualization. And this exists already for a long time, but this is kind of things that you can apply, like to basically, yeah, find images that excite a neuron as much as possible, and then you can play with multiple units at the same time and trying to find images that excite both of them, and so on, right? You can then make all sorts of fun extensions on this, but that's the basic idea. What you can also do is you can take the activations of a convolutional unit or the activation right before you go to your fully connected network, which is then typically a vector that you get after a global average pooling step, and then applying another sort of embedding technique, a dimensionality reduction technique, which we will see next time probably, to kind of take all of the input images that you have, pass them up until somewhere halfway of your network, take the activation vector out of that network, embed it into a two-dimensional space, and then it can also allow you to explore the way how your model is working in something which is a bit more convenient than that original high-dimensional space that you had. Now, let's say that you're looking at a particular image and you say, okay, fine, now I have confirmed that there are filters in my network that love to see flowers. Okay, good. But still, if I look at a single particular image, my network says that it's seeing a breed of dog here, but is it really looking then at the correct parts? What you could do is you could try to first identify a filter, a unit in your network that loves to see dogs, and then maybe applying this deconvolution step that we just saw to kind of make a heat map of, are you looking at the correct parts? But that would cause you that you need to hunt for a particular filter in this network. And it's not always the case that every filter matches exactly with a particular class or concept that you have. Sometimes it's multiple filters working in tandem as well, right? So it will not always be easy. So how do we figure out, given an input image, are you looking at the right part? Again, something simple that I can do is I take a square rectangle of gray values, the average value, and I just slide it over my image, and I ask the network, please predict, please predict, please predict. And normally what I would expect, if I slide the gray rectangle over the face of this dog over here, that suddenly my network will not be capable anymore to see the dog anymore. And I just then plot a heat map over my original image, showing, look, if I hide away this part, then my model makes a larger mistake, or then it fails to see the object of interest. And early attempts, what people found, for instance, is that for ImageNet, for a lot of pre-trained models, even although they're quite good at seeing a husky, what they're actually looking at is not a dog, they're looking at the snow in the background. Another particular annoying class in ImageNet is that of fish. If you inspect models, what do they like to see if they need to predict fish? They like to see hands, fingers, because most of the pictures in ImageNet of a fish is of a person holding a fish, a fisherman that has just caught a fish. So that's how you can uncover these things and how you can inspect these things. Again, here too, you can try to approach this as an optimization problem. Very similarly as what we have done previously, it's kind of like an adversarial attack where you say, okay, what are the parts of this image that I need to change so that you don't see a panda anymore or a penguin, but you stop seeing a penguin, right? And here too, I'm probably going to try to make sure that these changes are as small as possible. And here preferably also, and this is not necessarily the case with every adversarial attack, also keep the changes close to each other as possible, because making a change here and making a change here and making a change there, that's not going to give me a nice looking heat map. So also here I would like to make sure that the changes that I make have a nice Gaussian distribution, for instance, around a central point. And I also incorporate that into my loss function. Just like with these activation atlases, so embeddings already kind of mentioned, so what we can do is, but we still need to see embeddings to fully understand what's happening here, but embedding is basically a mechanism to perform dimensionality reduction, but even starting from extremely high dimensional instances. So let's say that you have something, a dimensionality reduction technique, which is relatively good at converting something high dimensional into a two-dimensional layout. Well, there are a couple of things that you can do. You can say, well, let's just start from the images that I have, and let me create an embedding out of them by putting them in 2D space, for instance, or 3D space, but in a lower dimensional space. In an unsupervised manner, what you will typically see is that embedding solutions that you get is they utilize one axis for the brightness of your images and another one of the hue of your images. So if you then plot your images in a plot, you would see that all the darker ones are over here, or the lighter ones are over there, the red ones are over here, the green ones are over there, for instance. What we could also do, like I said, is we could take the previous to last activation vector of numbers from our CNN model, for instance, which is also something high dimensional, and we could try to slap that into our 2D space. And again, we know which input image generated or created that activation vector, so we can still plot images in a scatter plot as well. There, typically, you will find, if you compare them with something that works in an unsupervised way, is that typically it will have separated your classes that you wish to predict more of with one another, because there, of course, your network has been trained in a downstream manner to try to establish this linear separability of the different classes that you have. So it's trained in a more supervised manner. So your embedding space will look different depending on whether you extract vectors from a model or whether you just start with images without any model to begin with. And then what you can also do is you can also still apply Lime and Shapley values as well. And with Lime, we saw the way how they do this is by creating supergroups of pixels. In the case of Shapley, what it will do, well, is it will basically utilize or inspect every pixel separately, right? Because every pixel is an input feature, and so you will get a Shapley value for each pixel in the input image. And then, of course, you can visualize this, and you can keep track of this again throughout the different layers of your neural network. And then you can visualize the parts that had a large or a positive contribution and parts that had a negative contribution. Always interpretable? Not fully, right? Because, yeah, if you look at this, it's predicting surprise. And the things that contributed positively, or maybe here around the eyes a bit, right? The eyebrows, but it's not like you get a super clear one-to-one kind of easy to understand interpretation, as was the case for tabular data where it was way easier. So maybe here the idea of Lime, of first creating supergroups, is maybe not that bad, but typically harder to do this. Now that we have already spoken about this idea of we could basically take a unit in our network and try to optimize an image in such a way that it excites it as much as possible. We have just utilized this to kind of understand what units like to look at. Obviously, this in itself, you can give a fancy name and you can call something like Deep Dream. And when you expand it a little bit, you can get something generative out of here. And the way how you can make this a bit more generative, here it starts with random noise. But what you could do, for instance, is let's say that you have identified already a filter that really gets excited by the presence of bananas. What could you do then? You could take some middle ground between this approach and this approach, where you say, well, I'm going to start with a real picture that I have, a face of someone, right? And I'm going to optimize changes to be made to this picture. And again, in my loss function, I'm going to try to keep these changes not too extreme, right? I still want to keep the original image, so I'm going to have, again, some L2 loss component on top of there. And I will have an excitement loss component on top of here as well, which says, okay, but the changes that you make need to be such that they excite this particular unit heavily. I let that run for a while. What is the outcome that you get is you get a face where bananas are growing out of the face and stuff like that because it's exciting this particular unit. Maybe you can do that not just based on the excitement of one unit, but you can do that based on the excitement of a couple of units, right? Which image do I get if I excite the banana unit and the house unit at the same time, right? And you get an image, and I start with random noise. Then you get an image where you can see both bananas, and it looks like a bit of a dream of this network. So this was a very early approach to generate images. The problem with these early generative approaches is that you don't have a lot of room towards guidance, right? It's not that you can type in a prompt and say, give me a picture full of bananas. it's you're using a pre-trained model in a specific way. You're trying to detect a filter that has learned a particular concept that you like, and then you try to excite that filter the most and change an image based on that. But we are not quite, or this early approach was not quite at the point where you could just type what you wanted to see. Like today, we have with the image diffusion models that we utilize nowadays. But this was a very early attempt at generation like this. And then you can do this deep dream for the original image and a couple of downscaled versions of this image, and then at the end you overlay them on top of each other again to make the result even nicer looking. But you get things that already look pretty interesting like that. Another related or in the same kind of era, what people also came up with is, okay, and these were these very early face swap apps and stuff like that, is I have a content picture. That's the picture in which I would like to keep the content, like a selfie that I took of myself. And I have a style picture, a picture that represents like the style that I would like to apply on my content picture. Like my content picture is I am in a landscape and I took this beautiful landscape photograph, and I would like to have this in the style of the painting The Scream. And then the result I expect to get is something on the right-hand side. Is there a way how I can have a model do this for me? And again, the approach is very similar to that of Deep Dream as well. So the idea here is that I'm going to basically feed these three images that I have throughout my network. And you can do that one after the other, or you can basically stitch them together. The result is pretty equivalent. So let us say that we will follow the stitching approach. And now I basically have an image that has three parts. The top part is the content image, then the style image that you have given me, and then basically the resulting image R. And they need to have preferably the same size, and the reason why I can stitch them together is probably I used a fully convolutional neural network instead of the ones where I have like a max pooling going on and stuff like that, but okay, we have seen how you can make that work. What will I do? My content image, that's my selfie, I can't change anything in there. I can push it forward through my network, and I can see which convoluted outputs that I get. Right? So here too, if I push my image through neurons like these, here I know that my output map is going to have the same width and height because I'm using padding, right? And same padding or something like that. So also here, I will have something that has a part for the content, for the style, and for the result. And I have that for every filter in my network. But I can't really change the content image. So that will stay the same. Right? I can pre-calculate that and keep track of content outputs that I have for my filters. Same for the style image. These are passed through as well, but that also just leads to convolved outputs everywhere. So I can also keep track of those. So again, the only thing that I can basically change is I have access to the pixels of this resulting part of the image. And I can also push them through my pre-trained network. I'm not changing the weights of this network anymore. It's pre-trained, right? It has already been trained on a large data set. I've downloaded it from the internet or whatever. And I'm going to compare, and I will say, okay, I'm going to inspect some filters and take a look at how they created the convolved part for the resulting image. And I will try to perform some sort of comparison in terms of style. Are you similar to the style part of the convolved output? And I will do something similar for the content, but then I'm going to inspect content rather than style. So again, it will boil down to comparing two convolved outputs with one another. So again, the question here is going to be, which loss function can I utilize to perform this comparison with, right? So content loss says, okay, compare the resulting convolved output with your content that you get there. And here, this is pretty simple. We just use the sum of squared errors to do so. We don't do this just with a single filter. Typically, we do that for all the filters in a certain layer. So we will take a whole layer and we inspect every filter. We calculate the sum of squared errors between its convolved output for the resulting image and for the content image. Typically, you use a layer a bit later in the network, a higher level layer, because for content, we're looking at content. We are probably not so interested in basic shape and texture and edges. We are already interested in more global structure and objects that need to match. Style loss then is where we try to compare the resulting image with style, and there typically we check the units in a lower level layer of the network. Because for style, well, there it's not so much of an issue if the painting of Picasso that I gave was of a cat, and you gave me a selfie. I don't want to retain the cats there. I basically just want to retain the texture of Picasso and the general style of Picasso, which is more, I can learn that from these earlier units in my network. So also there, I'm going to compare my resulting convolved output with the resulting part for the style image and see how far away that these two are from one another. Again, I could also utilize the sum of squared errors there, but typically for this kind of style comparisons, people use the Gram matrix, which is basically the dot product between A and A transposed. But other things have been tried as well. So I basically have a layer where I contrast the resulting convolved outputs with that of the content, and then I do it in another layer for the style part. And then again, I have a continuity loss or a total variance loss where I make sure that here, if I compare a pixel with its neighbors, that the values do not change too drastically also, because I want to keep the image coherent. And then you get a result where if you take this as the content image and this as the style image, and you pick your layers correctly where you perform this comparison, so this requires quite some amount of fine-tuning, and you basically need to set different weights for all of these comparisons and maybe even different layers and so on. But if you fine-tune this a bit, you can get results that look exactly like this, all coming or also coming from a pre-trained CNN. We are not retraining the CNN at any point, we're basically just using it kind of to guide the optimization process of a combined image, right? And you might wonder, why do you need a CNN to begin with? Why not just apply a loss metric where you contrast the sum of squared errors with this resulting image between the content image directly, right? Why don't you just do this directly on the image itself that you have? You could, but of course it's way harder to compare a high resolution image directly in this way, rather than first splitting up this into several units that have already learned how to separate out the presence of different concepts, right? And so which are probably better suited to apply this distance metric on than it is on your original image. This is also less dimensional typically, or in terms of values that you get here, they're nicely between 0 and 1 for every convolved output, versus here you're working still with color images, so they have a depth of 3, so you need to figure out in which color space that you want to work and so on. So here we use the network to kind of first create again some sort of representation for us, because these are basic representations of this image, where these sort of comparisons or distances are easier to execute on. Right? Which is why you use a pre-trained CNN there. Another architecture which can lead us to something which is generative is that of the autoencoder. Something that looks completely, well, not different, but a little bit of an aside. In a standard setup, an autoencoder is an architecture that looks schematically, as you see here on the slide, which looks like a funnel, which implements some sort of a bottleneck. It can be these circles that you see, these could be fully connected layers, but again, this could be something that performs convolutions to encode and then deconvolutions to construct an image again. Something like the UNet that we just saw is kind of also this form of architecture. Standard with an autoencoder is that you utilize them, or in a lot of cases, you utilize them in an unsupervised manner, where you do not need labels. So contrary to UNet, which we utilize to perform image segmentation, here basically you don't need to even have labels, or that's in a lot of cases how autoencoders get utilized. Why? Because they basically will give it a certain input, something tabular or an image, and we will ask it on the output side, what we expect from an autoencoder, hence the name auto, self, is that it's capable to give me exactly the same output as what I gave it on the input side. Now you might say, well, that's an easy task, right? How difficult could it be to learn to give the exact same output as what you got in? The challenging part here is, of course, this bottleneck that you have placed in, right? And you say, well, sure, we start from 200 features, but at some point internally, these are being squeezed to only 2 activation values. So the encoder part, the left-hand side of this network, needs to learn how to create, how to compress, or how to learn to compress input data in such a way that the decoder, which is the right-hand side of the network, from this limited set of values is able to reconstruct the original again. Hence why learning in a lot of cases, as we say, learning boils down to finding good representations, which is what these two values basically then are in the middle. These are ways that we can represent something that started off as being high dimensional as a feature vector, which has typically less dimensionality and less sparsity. So that is what it means to find good representations. But it's also about compression in a lot of cases, to compress your world knowledge down into a limited set of numbers. What can we do with this? A couple of things. What we can then do, let's say in the case of tabular data, one way how you can utilize this is to say I throw away the decoder part when I'm done, but I'm going to take these two activations of these gray neurons at the end, and I have a form of dimensionality reduction then. I can then stick in new input data and ask this thing, please reduce the dimensions for me. You will get something with this that is then very equivalent to PCA. Except with PCA, here you can choose the basis more freely of your projection, so it's a little bit less strict than what PCA would give you. What's another thing that you can do? You can say, well, if I now have a data set of instances, and I all throw them in, and I look at what my network generates on the output side, and I compare how good the reconstruction was. In other words, I calculate the reconstruction loss per instance, which can just be MSE or something like that. For instances which show up a lot in training data, or instances that happen a lot, probably your network will do a good job at reconstructing those. Because these occur a lot, if you would make mistakes there, you're gonna incur a lot of loss during training, so probably your network has learned to reconstruct the common cases pretty well. For instances which are anomalies, that are outliers, that are noisy, that do not occur a lot, there probably your network will have learned, I will probably don't need to do such a good job on those because anyway, they only rarely happen, right? So then if you have a new bunch of instances or you use those instances again, you take a look at the reconstruction loss, you can interpret that reconstruction loss as a measure for how anomalous that this instance is. So this is already one way to do anomaly detection as well. And what you can also do, and that's the generative part, except in theory this would be sounds like it's, well, first of all, what you can also do is you can change this approach a little bit, and you say, well, instead of expecting that you give me the exact same output as what I gave you as the input, I'm going to change up the task a little bit. And I'm going to start with images that I have gathered which all look normal, and I'm going to add a bit noise to them. And I'm going to give the noise as the input, the noisy image, and I'm going to ask you to reconstruct the image with the noise removed from them. Then what you have built effectively is a noise removal autoencoder, right? And then you can build something similar, not just for denoising, but for motion deblurring. What you need is just a whole bunch of images, and adding blur, you can do that with Photoshop, right? So you don't need to go out and find images that look like this. You can add that yourself to the images that you already have. It's easy to add motion blur and then teach a network, now unlearn the motion blur. And then tomorrow, if you take a picture with your camera that looks like this, you can ask the network to create it into something like this. Same for low light, same for deraining, things like that. You can add artificial raindrops on top of an image to create your training set of images to utilize. So then your input is not exactly the same as the output. Now, if we look at this thing, and we would say, okay, let's say that we sample just two numbers here. I have two activations here, or here I have a mini grid of pixels, and I just take a random one. And I ask the decoder, what does this look like? Would I be able, if I have trained this thing on a whole bunch of cat images, to then make new cats for me by just sampling from this latent space that I have there? In theory, yes, but to have that work, we need to do something else, because out of the box, autoencoders will not be good generative models. There is a link to PCA, as already discussed. So with the encoder and when the encoder and the decoder only have one layer with a linear activation function, then it's the same as PCA, right? So the way how this is more flexible than PCA is because it doesn't need to have only one layer, right? And it doesn't need to have a linear activation function necessarily. But if you would set up an autoencoder where you only have one hidden layer in the encoder and the decoder, and you use linear activation functions, then you get PCA here. It's basically one of the solutions, because you can have several bases that describe the same optimal subspace, but it's equivalent to the expressive power, at least, that PCA gives you. This is anomaly detection, what I had already mentioned. You can take a look at the reconstruction error and so on. What you could also do, by the way, if you want to do anomaly detection, is that you first feed in all of your instances and you again take the dimensionality reduced version of your instances, and you then train a simple classification model to perform, if you have labels, to perform some sort of classification with. Later we will compare this approach to isolation forests, for instance, and to other approaches. Okay. Generative. What doesn't, or what's the issue here? Ideally, I would like to sample an activation vector in this middle part in latent space and then give that to the decoder and say, please generate me a believable looking data instance from that, like the picture of a cat, for instance. That doesn't work with a normal autoencoder, and instead you need to use an adaptation or a small change to this kind of idea, which is called the variational autoencoder. So here you jump from an autoencoder to a VAE. Why is that? In a normal autoencoder, let's say, well, we want to make this thing not just the same as a PCA, right? But we want to make it deep with multiple layers and nonlinear because we are trying to learn how to construct and to reconstruct images, let's say. Which if you would just apply PCA on images, yeah, you would reduce their dimensionality, but it's not, let's say that if you would only keep the two principal components of that PCA result, and you would then pick a point in the two-dimensional space and ask PCA to apply the linear transformation to reconstruct an image from that, it's probably not going to look like a believable data element anymore. So on the one hand, we want to say, look, we are going to not just have a single layer, we'll have a pretty deep autoencoder. Secondly, our activation function, we're going to use values in there and so on. We're not going to keep that linear because we want to learn all of those interesting nonlinearities that are at play there. But when we do this, right, this dimensionality reduction that we're trying to learn, where we want to focus on decreasing the reconstruction loss as much as possible, this takes away from us the fact that our latent space is generative. And the reason why is, imagine that I have an autoencoder which is powerful enough. So I start from an input and I have a lot of layers in the middle. And these could be CNN units and deconf units. But in the extreme, I could basically squeeze this down to the extreme result where here in the middle, I have a single number. And where I basically ask my encoder, encode in such a way that this becomes a single number, that your image that you gave me is effectively a number, and that from this number, you need to decode the result of again. On your training data, can I do this in such a way that your reconstruction loss becomes 0, even if I just give you a single number? Well, yeah, you can horribly overfit. Right? You could basically decide, okay, if what you give me is a one-dimensional line, and I need to pick numbers on there, yeah, I'm just going to assign for each image a specific number, and I'm going to place it on this line. And if you make me deep enough, I will be able to do that. Then the next time you ask me, what is this number? I can perfectly reconstruct you the original image from there, because I've basically overfitted all of this stuff in my weights. But what you can't really do is then, if all of these are images of cats that I have, is that you would say, but now if I would start with this number, please generate me an image from that. So this interpolation thing will be completely gone. There will nothing meaningful that comes out of there. So what I would like to do is I would like to figure out a way where I can teach my autoencoder, or I can incorporate in the loss somehow, where I can say, look, it's not only this reconstruction that you need to get down, because if I make you fancy enough, then you're just going to overfit. I also want to make sure that the positions in between what you have embedded in your latent space based on the training examples, that they also somewhat make sense, right? I would expect that if I take the middle point between this number and this number, that the result that I construct from here, that this is going to look something which is in the middle of this image and this image. And so I should also punish you on that. If you fail to do so, I should also punish you on this aspect as well. So what this means is, again, I should make sure that my latent space, this one-dimensional or two-dimensional or n-dimensional representation that I'm building here, is regular enough. So again, there will be that idea of regularization that we are going to apply. And that's exactly what makes a variational autoencoder variational. There is another thing that we will change for this regularization to work, and that is we'll have to change our output or intermediate output to not just be a single point, a vector of numbers, right? Here I just had a single scalar, a vector with one number, but again, if I have two units in the middle like we had here, then basically I'm encoding to a vector of two numbers, right? So I'm basically going to two-dimensional space. So that is what I do with a normal autoencoder. With a variational autoencoder, I'm going to change this up. And I'm going to encode my intermediate representation, not as a single point in n-dimensional space, but I'm going to encode it as a distribution over the latent space. So I'm basically going to learn, for my n dimensions that I plan to encoding, a mean and standard deviations. So now, if before I said, well, I'm going to create a funnel shape in such a way that here I have two units, and hence they both output a single number as an activation, now I'm going to set up a funnel shape where both of these units, actually I have, now for each I have two of them, one predicting me a mean, and one predicting me a standard deviation. So in the one-dimensional case, what I'm doing now is I'm not, with this intermediate layer, figuring out what is the exact number that I should map the input to. I'm basically learning the position of the mean and a standard deviation of a Gaussian distribution. So I'm learning distributions across of this line. And in 2 dimensions, these will look like ellipsoids, and in 3 dimensions, they will look like bubbles and so on, right? But in the one-dimensional case, I'm learning a mean and a standard deviation like this. Okay, that's for the encoding side. So the encoder now, when I give it an input image, it gives me back a mean and a standard deviation. So it gives me a Gaussian on this one-dimensional line. How does the decoder part work? Because the decoder part before had to go from this single number in this case and reconstruct an image off of that. Now I basically have a mean and a standard deviation. So how do I pass this on to the decoder part? I just sample from it. So during training or at inference even, I know the Gaussian that my encoder has given me, and I just sample a value out of that. And then I have a single number again that I can give to my decoder like previously. So that's an additional in-between sampling step. So typically we assume these distributions to be Gaussian distributions, so I expect my bottleneck layer to return the mean and the covariance matrix, basically, if you work in a 2-dimensional or multi-dimensional bottleneck layer. So what does that mean? Okay, to reflect one more time. Let's say that we make our bottleneck again from 2-dimensional autoencoder to variational autoencoder, and I need to keep it 2-dimensional, otherwise it becomes hard to draw, right? That means that now for every image that I feed this thing, it's going to learn which distribution, which Gaussian maps to every input that I have. And hopefully this will already make it, and then when going to the decoder part, I basically sample from this distribution, right? And I get two numbers, x1 and x2, and from there I have the decoder part and I reconstruct my image again. And you can start to, or hopefully you can start to see what these Gaussians are meant to do here, right? They are meant to learn better, like, well, an image is not just encoded as a single point in this 2-dimensional space, but they also have like a surrounding neighborhood. And this will allow, if I have two images that are similar to one another, that if I interpolate in the middle of them, that I will get something that is probably better going to be a mix between these two, right? Because these distributions, they will of course also be able to overlap with one another. And hopefully my model learns that this image here in the middle should then correspond 50% with this and 50% with that one. So the generations that I get will start to look more believable. But there is an additional step, and now we come back to the loss function that we need to add in. Because if I just do this, I still have the same problem as what I had before, right? If reconstruction error is the only thing that I want to minimize even if I learn distributions such as these and I'm sampling from them for the decoder part, what's the best that my encoder can learn how to do? Is trying to make this distribution tinier and tinier around every image, right? That's the best for your reconstruction. Then all of your data points, they don't mingle with one another, and you have a perfect reconstruction again, right? So here, I basically have to punish somehow, and I have to say, okay, you're free to do so if that really helps you for your reconstruction error. That's my main loss, is I want to minimize, or I want to, my main loss part is a reconstruction error, which is basically just sum of squared errors between the input and the output that you generated me, right? And I'm going to add in, yeah, again, our good old friend, some form of regularization. But now, because I'm not working with weights, really, it's not really the weights in this thing that I want to regularize. I could also regularize the weights. All the internal weights here, I could also try to keep to 0 as much as possible. But what I especially want to look at is this mean and covariance matrix that you're outputting me. And I kind of know that the tinier that you make this around this point, the less happy that I will be. There needs to be a trade-off. I want these distributions to be wide and to overlap one another. Or what I could say, since you're going to position yourself in this two-dimensional space anyway, I could say, look, kind of the starting point where I expect a normal distribution to fall in is that it looks like this. The normal Gaussian distribution centered around 0 with a standard deviation of 1. If you give me exactly this, then I'm not going to punish you, I'm not going to regularize you too heavily, right, or at all. It would be as your weight in a normal neural network would be equal to 0, right? Well, this is basically the standard case for a distribution that you can fit or reconstruct. But of course, if you would say, yeah, but if we plot every input image to be this distribution, and then we sample from this to generate the output image, they're all going to be the same. I will not be able to reconstruct anything anymore. So of course you will have to move these distributions around to bring your reconstruction loss down. But then again, it's a trade-off. Loss is reconstruction error plus some lambda. And now not probably all the weights squared, because that's not what we're doing. Probably plus some lambda, the sum of all the distributions that you generated me compared to this standard normal distribution. What do we have that can compare two distributions with one another? In evaluation, I already mentioned it. KL divergence is one thing that you could utilize. JS divergence is another thing that you could utilize as well. Earth's mover distance is another one that you could utilize. For generative adversarial networks, this one gets utilized, for instance, a lot. But some way how you can compare how much does the distribution that you are predicting for this instance, how much does that differ from the normal distribution? And then you get something where if you do sample in this latent space, that you can suddenly start to generate images that are believable, such as these, for instance. So this is a variational autoencoder where you start with a whole bunch of faces. You basically try to learn how to reconstruct all of these. You sample from the latent space, basically, or you sample in between the position of two faces. You sample yourself a vector of two numbers or n numbers in latent space. And then you ask the decoder part, now please tell me which face comes out of there. Now you have a phase generation model by doing this. This idea of a variational autoencoder is still present even if you look at the main fancy image generation models of today, like Stable Diffusion and Flux and stuff like that. They also still utilize a variational autoencoder, but together with some other insights. But they're still there as a backbone, so pre-trained variational autoencoders are still quite common. What we don't really have here is you could set this up, and if you like to generate cats, you first download a data set of cats, and then you build this thing. Normally, or what we still need to get towards is something where we start from a VAE, where we have stuck in all the images of the internet that we have, and then something again to guide this, where we say, no, this time I want a face, or this time I want a cat. So again, we need some kind of prompt mechanism that we still lack, but if you know what it is that you want to generate, you can train models like these. Next up, or as a last generative model for now, at least, is that of a generative adversarial network. And here the idea is that we're going to build two models. And one is called a discriminator and one is called a generator. And again, it's an interesting idea, which is not that difficult to understand. You start with, again, a bunch of images that you have collected, dogs, so images that you like. And again, same question, how can I generate images that feel like they would have come from the same set? Not using a VAE this time, but using something else. You will have a generator again, which job it is, given, again, a randomly vector, a randomly sampled vector that I give you from a latent space that I'm going to construct. So again, it's quite similar. Again, we're trying to find a gradient over this latent space, but in a different way of training. Given a noisy vector that I sample, or given a vector that I sample, the generator's job is going to be to convert that vector into something that looks like a dog. And then the discriminator, there I'm going to take a bunch of real dog faces or dog pictures that I have, and I'm going to mix them in with generated images coming from my generator. And I'm going to ask my discriminator, are you capable to spot which of these are fake and which of these are real? And depending on what the discriminator tells me, I'm going to update either the weights of the discriminator or of the generator. For the cases where my discriminator gets it right, and is able to say, this image was generated, but is a fake one, right? I'm capable to update my generator with that information. Especially because for some images, my generator will have been able to fool the discriminator a bit more than for other images. So it kind of knows the gradient that it should go towards. What should it focus more on to look more like a dog image? If my discriminator gets it wrong, then of course I'm going to utilize its loss to update the discriminator with. You have been fooled, so maybe adjust your weights accordingly so that next mini batch you do a better job at spotting the real images from the generated ones. And these two are in a competition with one another. So in the beginning they're both dumb. The generator is just generating random pictures and the discriminator is getting fooled. But because the discriminator is getting fooled, it becomes a bit better. And because the discriminator becomes a bit better, we are able to tell, hey, generator, you're not doing as good of a job anymore. But the images where there was some brown splotch in the middle, there the discriminator had a little bit more trouble. So try to do more of that. So stepwise, try to generate more and more. Try to learn how to construct, again, a gradient in your latent space so that you can convert this to samples that look believable. Now, that's the nice theory. In practice, however, these models are extremely hard to train because you're trying to find some Nash equilibrium in some sort of a prisoner's dilemma game in a two-player non-cooperative game. And it's very hard. Either what can happen is that either your discriminator becomes, by random chance, becomes good enough too rapidly so that your generator basically cannot learn anything anymore, because if the discriminator is perfect, then the generator can't learn anymore. Or your generator gets stuck in a mode where no matter which vector that you start from, it always outputs the exact same image, because it has found by luck again that this was able to fool the discriminator and things also get stuck. So this is the theory, but in practice these type of models are extremely hard to train. Until at some point, so there have been some tricks that people figured out, until 2017, where again there was a way how people kept track of the performance of these models. So the loss function in this case was typically defined of, again, the KL divergence between how far away are the generated examples versus the real-life examples or the real examples. The Wasserstein GAN, basically what they propose is to switch out this distribution similarity metric, not by using KL or JS, but by using the Earth-Smoother distance. And that seemed to work pretty well in the case of a GAN, and that's still what the majority of these style of models utilize. Still, these were not the easiest models to train, but for the longest amount of time, these were the best type of models that we had to generate believable, high-resolution images with AI models. Not really yet a prompting mechanism, but this was something that for a while we thought, well, this is the best that we have. And people played around with architectures such as CycleGAN here as well, where you have a generator that does not start with a noisy vector, but you have photos of winter images and photos of summer images, and you have one generator where you give it a picture of a winter image, and you ask it to convert it into a summer image. And the other generator, you give it pictures of summer images, and you ask it to convert it to a winter version of the image. And likewise, you have two discriminators that both try to figure out, did you try to fake me, yes or no? Is this real summer or is this fake summer? Is this real winter or is this fake winter? And again, you train them in tandem like this, and then if you apply this, you get generators where you can give a picture of a zebra, and you can convert it into a picture of a horse, and vice versa. You can give the other generator a picture of a horse, and it can convert it back to you in a picture of a zebra. So for a while, these were the best models that we had, and we looked at this, and all of us said, wow, amazing, fantastic. Now we ask Gemini Flash, and it does it for us, so just to show how far the things have come along. Main problem with this is that for high-resolution pictures, this GAN thing was extremely hard to train. So NVIDIA came up with an approach that they called StyleGAN, where they train these generators in a progressive fashion, and where they say, well, we're first going to generate a generator, or train a generator, which task it is to generate a believable but low-resolution picture. And then if that one works relatively well, we're going to bring in a second one into the mix, which job it is to learn how to upscale this picture, to start with a low resolution one and make a higher resolution version out of it. And we do that for a couple of rounds, so we can basically stepwise train these guys together, and then in the end we have something that can generate high resolution pictures for us. And these models are known as StyleGAN, and these are models that you can actually run on your own computer, and these are what led to websites such as This Person Does Not Exist, where for a while everybody thought, wow, amazing, this is so believable, but again, now we will say, yeah, but it's all faces, it's not a full body shape, there is no prompt here, they all look, different enough, but the composition is exactly the same. Today we can make videos given by models, so this is not really that special to us anymore. But at least it's something that was executable on a normal machine, and up until 2021 was still commonly utilized. And also these early attempts, like edges to photo and this to that, were all based on similar types of models. Like I said, up until the 2020s, we utilized StyleGANs for uploading a picture of a painting, and then the painting could talk to you and things like that. The next step, or the next type of model, and then we come to the current lineage of models that we utilize, are the diffusion-based models. And diffusion is yet another mechanism to generate images that look like they could be real. And in the case of diffusion, what we will basically learn is, what if I start with a completely noisy image again, and I directly learn how to stepwise remove pieces of noise from that image until I end up with something that looks real. So it's always starting with something noisy, something that you sample from latent space, and learning how to construct something believable out of that. Okay, I see it's 4 o'clock. I think that was also quite a lot for one session, actually. So we will finish off this last diffusion part at the start of next week's course.